Section 12.1, one-way ANOVA. Okay, so ANOVA is the separation of variance ascribable to one group's causes from the variance ascribable to the other group. ANOVA is based on the test statistic, on the statistic F. We assume the observations are independent and the parent population for which the observations are taken are normal, and the various treatment and environmental effects are additive in nature. So again, Fisher was a agronomist, so some terminology will be terminology from agriculture. A lot of other people use this type of technique. And so some of the terminology that you'll also hear are from other fields, such as psychology and medicine and all that. And so there'll be several, like environmental effects and all that. There'll be several sort of terms that can be interchangeable depending upon your field. And I'll kind of show it as I go through this. So the basic questions that we're trying to answer with ANOVA are, well, are all means from several populations equal? Are all means from several treatments on one population equal? Do several treatments have a common effect? So we looked at comparing the means from two independent samples previously. Now we're going to look at we will test the equality of more than two means using this one-way analysis of variance, ANOVA. So let's recall my F distribution. So an F distribution is skewed to the right. It is non-negative, and it depends upon 2 degrees of freedom: the degree of freedom of the numerator and the degree of freedom of the denominator. And so the probability density function for my F distribution was that gamma of nu1 plus nu2 over 2 divided by gamma of nu1 over 2 times gamma of nu2 over 2 times nu1 over nu2 to the power nu1 over 2, all times f to the power of nu1 over 2 minus 1 divided by 1 plus nu1 over nu2f, that whole quantity to the power of nu1 plus nu2 over 2. The expected value of f is nu2 over nu2 minus 2, which is greater than 1 for nu2 being greater than 2. The mode is nu2 times nu1 minus 2 divided by nu1 times the quantity nu2 plus 2, which is less than 1. And the skewness was greater than 0. So the test statistic for testing two variances was that F is S1 squared over sigma sub 1 squared divided by S of 2 squared over sigma sub 2 squared. If we're testing the quality of two variances, then the sigma sub 1 squared and sigma 2 squared, since we're assuming that they're equal, cancel. And so if we're testing that sigma sub 1 squared equals sigma sub 2 squared, then F, the test statistic F, is just equal to S1 squared over S2 squared. So the ratio of the sample variances, where S1 squared is greater than S2 squared, we're always doing a right tail test, only because if we're looking at a table. So if we're looking at a table, we make this assumption. Recall the Wilson-Hefferty approximation. A was equal to 2 over 9u2, B was equal to 2 over 9u1, C was bz squared minus quantity 1 minus b quantity squared. B is 1 minus a times 1 minus b. A is az squared minus the quantity 1 minus a squared. F was a negative b plus the sine of az times the square root of b squared minus ac over a cubed. And we had that z was equal to 1 minus a times the cube root of f minus the quantity 1 minus b divided by the square root of a times the cube root of f squared plus b. And so in one-way analysis of variance, the total variance is split into two components: the variation between classes and the variation within classes. And so the variation due to two different bases of classification known as treatments or factors. This type of variation is due to assignable causes, which can be detected and controlled. It involves finding variance of means. Next, the inherent variation of a random variable within observations of the class. This type of variation is due to chance. The variation within classes is calculated using all the sample data and is not affected by the difference of means. So one is, ascribable, we can find the means, the other isn't. And so looking at those two different ways, we can figure out, well, what, is there actually a difference in the mean? And so one-way analysis of variance is the method of testing the quality of several population means by analyzing the sample variances. And so one-way analysis of variance is used with data categorized with one factor or one treatment, which is a characteristic that allows us to distinguish different populations from one another. So the requirements are: the populations have approximately normal distributions. The populations have the same variance. The samples are simple random samples of quantitative data. The samples are independent of each other. The samples are from populations that are categorized in only one way. We'll be doing two-way ANOVA also, but in this section, they're categorized in only one way. So when we conclude that there's sufficient evidence to reject the claim of equal population means, we cannot just naively using ANOVA we cannot conclude from ANOVA that a particular mean is different. We will show you several different techniques to try to identify if specific means are different from the other means. Okay, so let's look at a particular example. So we're going to compare dataset A with dataset B. And dataset A is the same as dataset B, except for one fact. The sample 1 differs from the other sample 1 by 10. So I just added 10 to these values. All the data sets had the same sample size of 4. So these are all sample sizes of sample 4. Okay, so I have here that the sample size here is 4. The sample mean is 5.5. The sample variance is 3. The sample size is 4. Well, these are the same. The sample mean is 6. The sample variance is 2. And for this one, these are the same. The sample size is 4. The sample mean is 6. And the sample variance is 2. Here, for the first one, well, again, the sample size is the same, 4. The sample variance is the same, 3. But the sample mean is 15.5 as compared to 5.5. So everything else, so I look at everything here, everything is the same, all the numbers are the same, except for these numbers here. And the only thing that changes is that since I added 10 to everything, the sample mean has increased by 10. So, well, now the thing is, all the variances are the same. So how am I going to look at the variances and somehow from the variances determine that, that the means are different? So let's look at the variance between samples. So I'm going to look at the variance here between the samples. Okay, so I have here, well, there's if I look at the variance between the samples here, I have here, well, let's see, the sample size is 4. And if I look at the variance for the sampling distribution, these sample means, I get 0.333. Whereas for this one, I get 120.333. Let's look at the variance within the samples. And so let's just take the average of these. And so the average of 3, 2, and 2 is 2.3, which is the same over here. The pooled variance is the same because these variances are the same. Okay, so let's compute the test statistic, which is the ratio of the variance between the samples and the variance within the samples. And I get here 0.1428, but here I get 51.5724. Oh, okay, so I have a completely different F value. Now, if you look at the p-value corresponding to that, this has a much larger p-value as compared to this. Okay, so the degrees of freedom here. So the critical F is found by looking at a right tail test. So we're going to be doing a right tail test. My degrees of freedom are, well, K. We're going to be using K, the number of samples. So the degree of freedom for the numerator is K minus 1. And also n, the sample size. The denominator degree of freedom is K times n minus 1. And so notice this stuff here above, that the 3 samples in dataset A are identical, the 3 samples in dataset B, except that each value in sample 1 of dataset B is 10 more than corresponding value in dataset A. So again, these are 10 more than these values. Adding 10 to each data value in the first sample in dataset A has a significant difference on the test statistic, with F changing from 0.1428 to 51.5721. Adding 10 to each data value in the first sample of data set A has a dramatic effect on the p-value, which has changed from 0.8688, not significant, to 0.000018118, which is significant. The three sample means in data set A are very close, but so all these sample means here are all close to each other. But the sample means in data set B are not close. These are close to each other, but this is significantly different than these other means, which has affected your F, your test statistic. It has, decreased the value here of your p-value. Okay. So the sample variances in data set A and data set B were identical. So all these variances are the same. Same. The variance between the samples for data set A was 0.332, but for data set B was 120.332, indicating that the sample means in B are farther apart. So this was much larger than this. Therefore, the sample means are much further apart from each other as compared to the sample means from here. The variance within the sample is 2.33 for both data sets A and data set B. If you look at the average of these, well, they're the same. So since they're the same, obviously the average of them is going to be the same. Because the variance within the sample is not affected when we add a constant to every sample value. The change in the F test statistic and the p-value are ascribable only to a change in the mean, in the sample mean. This illustrates the key point underlying the method of one-way analysis of variance. The F test statistic is very sensitive to sample means, even though it is obtained through two different estimates of the common population variance. Okay, so, oh, well, I'll tell you that. So, the question is, well, is there a way to figure out which of these, so in here, it says that all these means are not the same. The question is, well, which one is different? So how do you figure out which of these are different? Obviously, this one is different, but how do you figure that out? Well, informally, you would construct box plot and examine any overlap to see if one or more of the box plot is very different from the others. You construct confidence intervals to estimate the means for each of the different samples, and then compare those confidence intervals to see if one or more of them does not overlap with the others. So those are the informal methods. The formal methods would include the range test that allow us to identify subsets of means that are not significantly different from each other. The multiple comparison test. So they use pairs of means, but they make different adjustments to overcome the problem of having significance level that increases as the number of individual tests increases. So the Bonferroni multiple comparison test. You would do, so this actually is a relatively complicated way of doing this. You would do a separate t-test for each pair of samples, but make adjustments described in the following steps. For an estimate of the variance that is common to all the involved populations, use the value of the mean square of the error, which uses all the available data. And so T would be the difference of the means. Remember, you're doing it for each pair. So for this particular pair, difference of the means divided by -0. You're assuming they're equal. Divided by the square of the mean square of the error times 1 over n1 plus 1 over n2. Again, you're estimating the population variance by the mean square of the error. After calculating the value of the test statistic for each particular pair of samples, find either the critical t value or the p value, but make the following adjustments to the overall significance level. So for the p value, use the test statistic t with nu equaling n minus k, where n is the total number of sample values and k is the number of samples. Then find the p value, but multiply it by the number of different possible pairings of the samples, of the two samples. For critical value, we find the critical values, adjust the significance level alpha by dividing it by the number of different possible pairings of two samples. Okay, so, and we'll be actually doing an example involving the Bonferroni comparison test. So recall from chapter 8, I believe, the t-test to test the equality of two means. We had the following hypothesis test. The null hypothesis is that mu1 was equal to mu2. The alternative hypothesis was that mu1 and mu2 are not both the same. And we had some level of significance alpha. And so we then needed to conduct a f-test to see if we're going to pool the populations or not. And so the f-test was used to determine if we were going to pool the population in testing the equality of two population means. And so f, since you're testing the equality, is the test statistic was just S1 squared over S2 squared, since the we assume that the ratio of the population variances are equal. Suppose we had the pooled case, that they were actually equal. Then we use the pooled variance, which was the following weighted average. So it was a weighted average where you weighted the variances, the sample variances, according to their degrees of freedom. And so the pooled variance was just nu1 times S1 squared plus nu2 times S2 squared over nu1 plus nu2. It was the sum of nu sub I S sub I squared over the sum of u sub I, which is, well, this is just going to be n1 minus 1, and this is n2 minus 1. So n1 minus 1 plus n2 minus 1. is n1 plus n2 minus 2. So it's n minus 2. So I can replace this by n minus 2. Matter of fact, if you had a whole bunch of these that you're adding up, well, notice that I kept just having a minus 1 for each of them, and I combined that. So nu was just equal to nu1 plus nu2, which was just n minus k. Okay, so where k is the quote-unquote number categories, in this case, 2 categories. So what do we do in ANOVA? But the same thing. So we're going to do sort of the same thing in ANOVA. Well, one way ANOVA. And so in ANOVA, well, we're going to be testing instead null hypothesis. Is mu1 equal to mu2 equal to mu3, equal to mu sub k? Alternative hypothesis. Not all the population means are the same. And alpha. And we're given some alpha. Okay, so we just logically extended this from 2 to k. Okay, so now the test statistic will be F is going to be the ratio of 2 sample variances. Oh, okay. There it is. So F here is the ratio of 2 sample variances. Now, we call it, well, the variation due to treatment and the variation due to error, or, well, again, between classes or within the classes. And so let's look at the variation with between the classes. And so the variation due to treatment. So the variation due to treatment is also sometimes called the variation between classes. So I'll interchange these, back and forth. I keep calling them one or the other. Okay, so it is the sum of n sub I times x sub I minus x bar squared over k minus 1. Oh, okay, so this is just the regular formula for variance. You just finding the variance here. The variance within classes, the variance due to the error, the variance within classes is the sum nu sub I s sub I squared over the sum of nu sub I. It's the same thing. It's the same exact formula we had for the pooled variance. So this is the pooled variance. So the standard error, the variance due to the error. So the variance due to the error, the variance within classes, is the pooled variance. Oh, so this is just the pooled variance. And of course, we saw that the sum of nu sub I was just n minus k. So sometimes we'll write it this way, where we replace the sum of all those nu sub i's by n minus k. Yeah, okay. So let me use the following notation. X sub I bar is just the sum of x over n for each category, just like what we did up here. And also we did that over here. S sub I squared is the variance with each category. Now, X bar. Sometimes they write this as X. I don't like this notation. So the notation that a lot of times is X bar bar. It's the average of the averages. It is the sum of n sub I, x sub I bar over the sum of n sub I. K is the number of categories. K minus 1 is the degrees of freedom among the categories. N is the sum of n sub I. It's the total sizes of all the samples. It's the total sample size, the total combined sample size. N minus K, the sum of nu sub I, is the total degrees of freedom within classes. And so the sum of squares between the classes, the sum of squares for the treatment, the sum of squares between the classes, between the groups, is the sum n sub I, x sub I bar minus x bar squared. The sum of squares within the groups, the sum of squares due to the error, the sum of squares within the group. So all these are notations that we'll be using. Is just the sum of nu I, s sub I squared. It's the numerator of the pooled variance. The mean sum of squares between the groups, the mean sum of squares between the groups, is the sum, well, it is the sum of squares between the groups divided by their degrees of freedom. And so it is the sum n sub I, x sub I bar minus x bar squared over k minus 1. The mean sum of squares within the group is, well, again, it's just the pooled variance. It is the sum nu sub I, s sub I squared over n minus k. So let's do an example. Use the classical ANOVA method to test a hypothesis. And so I have here the null hypothesis. Mu1 is equal to mu2 is equal to mu3. Alternative hypothesis. Not all the means are the same. Alpha equals 0.05. And so I have here that the mean for the first sample is 20.4 and standard deviation is 18.2 and sample size is 11. For the second sample, the sample mean is 38.3, sample standard deviation 15.1, sample size 10. For the third sample, the sample mean is 44.1, sample standard deviation 15.5, the sample size is 9. So let's determine the critical region. So I need to determine the degree of freedom for the numerator and denominator. And so the degree of freedom for your numerator is, well, the number of categories minus 1. And so in this case there, well, 1, 2, 3 of these. So 3 minus 1 is 2. So the degree of freedom of the numerator is 2. The degree of freedom of the denominator, the degree of freedom due to the error, is the sum of nu sub I. And so it's just equal to 10 plus 9 plus 8, 27. Or the grand total sample size. So that's 2030 minus the number of categories, 3. So 27. And so I have that my degree of freedom of the numerator is 2, of the denominator is 27, and we have alpha is 0.05, our critical value turns out to be somewhere around 3.3. And so now let us construct our ANOVA table. So I want to construct my ANOVA table. And so my source, I guess I'll call it treatment and error, or I could call it between groups and within groups. First, the easiest part to put is, well, my degrees of freedom. So let me do my degrees of freedom. Oh, sometimes this is denoted by DF. So sometimes nu, sometimes DF. In your ANOVA table. Okay, so, well, that's the easiest. So the numerator degree of freedom for your treatment is 2, for your error is 27. The degree of freedom between groups is 2, within groups is 27. So let's find the overall mean. So to find the overall mean, well, again, from chapter 3, section 3.1, well, we know what it is. We know the formula. And so to find it within groups. So I have all these means. Okay, so 11 times 20.4 plus 10 times 38.3 times plus 9 times 44.1. Well, that gives me the total sum divided by n. So you'd have to add these up. Okay, so you get, I guess I'll, there it is. And so 11 times 20.4 plus 10 times 38.3 plus 9 times 44.1 divided by, well, 30. 11 plus 10 plus 9 gave us 33.4766. So 6 is repeated forever. So now the sum of the squares due to the treatment, the sum of the squares between the groups is the sum of n sub I times x sub I bar minus x bar squared. So it is, well, let's see. Actually, let's see if I can do it this way. Yes, I can. Okay, so it is 11 times 20.4 minus the total 33.4766 squared plus 10 times 38.3 minus the 33.4766 squared plus 9 times the quantity 44.1 minus the 33.4766 squared, and you get 3,000, so 3129.333666. Okay, there. And so that's the sum of the squares between the groups. Now let's do the sum of squares, do the error within the groups. And so the sum of the squares due to the error, the sum of the squares within the group, is the sum of nu sub I, s sub I squared. It's the numerator of the pooled variance. So it's the pooled the numerator for the pooled variance. And so, let me, let's see if I can do this. I can't quite do it. Okay, so 10 times 18.2 squared plus 9 times 15.1 squared plus 8 times 15.5 squared. Okay. Is 7286.49. Okay, so I'll put that here. Okay, so now we're basically done. Okay, so now that we've done those two calculations, we'll quickly fill in the rest of this table. And so to figure out this number, I just divide this number by this number. And so I'll just divide the 3129.3336 divided by 2 to get 1564.66683. Next, I'll take the 7286.49 divided by 27 to get the 269.87. And then lastly, to calculate this number here, we take the 64.66683, divide it by the 269.8 to get the 5.797853.905. And that is my completed ANOVA table. So these first two were easy. These computations weren't too bad. I mean, this was each of these formulas we've seen before. So we've seen these formulas before, in chapter 3. So these were, formulas from chapter 3, now extended to this case. So use the formulas from chapter 3, like the pooled variance and things like that. The numerator from the formulas from chapter 3, and then divide. And then divide. And you're done. So my test statistic is 5.79, which is not, which is in the rejection region. Therefore, I reject the null hypothesis. And so I'm rejecting the null hypothesis, which was that all the means were equal. And so, no, there's insufficient statistical evidence to support the claim that all the means are the same. Any questions about this? So a lot of this is just notation. It's sort of horrible notation, but it's stuff that it's basically the stuff that we've done before in chapter 3. And of course, combining that with the knowledge we had from chapter 8, we sort of put all that together and we construct, once you have the ANOVA table, that everything is, well, actually, once you have these two, then everything follows really quickly. Use the classical rejection region ANOVA method. The ages of top executives in 3 major corporations are listed below. So Corporation 1, 49 to 62. Corporation 2, 61 to 54. Corporation 3, 56 to 48. Use the analysis of variance at the 0.01 level of significance to determine whether or not the average ages of the top executives at these corporations differ significantly. And so, null hypothesis. There are 3 corporations, so mu is mu1 equal to mu2 equal to mu3. Alternative hypothesis. Not all the means are the same. And alpha, by the way, you cannot write that would be wrong. So do not write that, because that's an incorrect statement. We're saying not all of them are the same. We're not. So at least one of them is different. And that's what we're saying. And we don't know which one it is. So, and again, alpha is 0.01. So let's use the TI-84 to do this. So I'm going to use the TI-84 to do this. We find that the critical value is 7.56. And, well, degree of freedom of the numerator is going to be 2. 1, 2, 3 minus 1 is 2. The denominator is 10. You can actually, let's see, 3, 6, 9, 12, 13 minus 1, 2, 3 is 10. Okay, so let's put all of our data into the TI-84. I'm just going to put corporation 1, the ages of the top executives in corporation 1 and L1, of corporation 2 and L2, corporation 3 and L3, and then we're just going to use ANOVA and then fill in the table from what we get from what's listed on the TI-84. Okay, so actually, I wonder if I can do it. Let me just check if I can do it using this calculator. I don't know if I can. I almost always, let me just check something. ANOVA. We have ANOVA here. Okay, so let's try to do this then. Okay, so let me try to use this emulator. I hope it does it okay. 49, 58, 55, 60, 62. Store that in L1. Let's do 61, 59, 58, 54. Store that in L2. 56, 63, 60, 48. Store that in L3. Okay, so now let's go to stat, test, and go all the way down to ANOVA. And let's do L1, L2, L3. So let's do all of them. Okay, so I have here F. My critical value. No, that's my test statistic. My test statistic F is 0.0810469 Okay, good. The p-value is 0.92274988818. Good. And now let's do the factor. Okay, so now let's do my factor. So this is also called, so here it's called factor. Same as treatment. Okay, so the factor. Degrees of fruit. So I'm going to fill in the ANOVA table. So degree of freedom is 2. Sum of squares is 4.1423076923. Now they have an extra 23 here. And the mean, so they'll be divided by 2 to get 2.0711538462. And now let's look at the error. Degree of freedom is 10. Sum of squares is 255.55. Divide that by 10 to get the mean sum of squares, which is the 25.555. The pooled variance, well, we don't actually need that. So, okay, so Oh, and they gave the p-value, which was this. Oh, and you can also find the p-value. It's always right-tailed. So 1 minus FCDF, you go from 0 to F. Degree of freedom of numerator is 2, and the denominator is 10. So you could also do 1 minus, let's 1 minus, go to distributions and FCDF. There it is. We're going from 0 to 0.08, 104, 69, 124. Degree of freedom of numerator is 2, denominator was 10. 0.92274988818, which of course they also gave you right here. So same p-value. Okay. So now let's look at this. So this number here, my test statistic is not in the rejection region. So I do not reject the null hypothesis. I didn't reject the null hypothesis. So there's insufficient statistical evidence to reject the claim that each of the means are the same. Maybe I should say yes. So again, my test statistic was calculated using, the ratio of two variances. Again, F is S1 squared over S2 squared. It was, again, the variance due to the treatment of the variance due to the, that's actually the variance. The variance due to the treatment of the variance due to the error. Or between and within. We keep switching between all these terms. And so, assuming the populations have the same variance, the F test statistic is the ratio of two estimates of variances. The variance between the samples based on the variation among the sample means, the variance within the sample based on the sample variances, not on the sample means. So when testing the equality for three or more populations, you should use analysis of variance. Do not use hypothesis tests within two samples at a time. Testing two samples at a time will require multiple hypothesis tests to be performed, and that would take a long time. And actually, you also have to adjust. You would need to adjust the depending on, if you're doing p-test, or let's assume you're doing the classical method, you'd have to adjust your level of significance due to the fact that you're doing this multiple times. And we'll actually do that for the Bonferroni, which actually does this. Okay, so let me give you a method to detect if we're able to figure out, if in the above example, or let's say the very first example we looked at, we saw that we could reject the null hypothesis. Now the question is, which of the means is different? And so the critical difference method, the least significant difference method, given alpha, the critical difference, the least significant difference between the ith mean and the jth mean is defined as the critical difference between the ith mean and jth mean is the t critical value times the standard error of the difference between the ith and the jth sample mean. It's the t critical value times the mean sum of squares within the sample, or the standard deviation, the variance for the variance between the variance due to error, times, well, again, this was an estimate of the population variance, so we took it out. So times 1 over n sub I plus 1 over n sub j, where my degrees of freedom here to calculate my critical value was n minus k. So we are assuming that the variance due to the error is an unbiased estimate of the error variance. If the difference x of I between the sample means for xi and xj, and let's take the ceiling of this, is greater than this critical difference, then there is a significant difference between the ith and jth mean. So then I can say that, well, these are actually different. The Bonferroni multiple comparison test. So this is where we said, don't do it because it gets really complicated. You do a separate t-test for each pair of samples. Use the value of the mean sum of squares within, which uses all the available sample data to estimate the population variance. And so, when we constructed our ANOVA table, notice that this was one of the things that we placed into one of the first things that we placed into the ANOVA table. Calculate the test statistic, T, x minus mu over sigma, just like always. Then calculate the mean sum of squares within. We'll use this as the estimate of the population variances. It is just, again, the pooled variance, the sum of nu sub I over s sub I squared over, the sum of nu sub I, or n minus k. And so, again, the variance for the sampling distribution, the difference of these two sample means, is just the sum of the variances for each of these sampling distributions, which is just sigma sub 1 squared over n1 plus sigma sub 2 squared over n2. I will just do the, I'll estimate each of these by the mean sum of squares within and factor it out. Then, for the critical value method, adjust alpha by dividing it by the number of possible pairings of the two samples. For the p-value method, multiply the p-value by the number of different possible pairings of the two samples. And so, say if there are 3 possible pairings, we would multiply by 3C2. And so it's always, so it'd be KC2 or whatever, how many you had. So let's do the following. Use the performance IQ scores listed below and the significance level alpha equaling 0.05 to test the claim that there that the three samples come from populations with means that are all the same. And so performance IQ scores of children, low blood lead level, 85, 100. Median blood lead level, 78, 85. High blood lead level, 93, 86. So let's, find the following. Well, for low blood lead level, the sample size was 78, mean 102.7, standard deviation 16.8. It's approximately normally distributed. There were potential low outliers of 51 and high outliers of 146, 149, but none of these are very far away from the other data. For the medium blood lead level, sample size 22, sample mean 94.1, sample standard deviation 15.5, is approximately normally distributed, and there are no outliers. For high blood lead levels, sample size 21, sample mean 94.2, sample standard deviation 11.4. Distribution is approximately normally distributed, and there are no outliers. Okay, so the three samples appear to come from populations that are approximately normal. This was looking at the normal quantile plots. Everything seemed okay. Three samples have standard deviations that are not radically different. We can treat the samples as simple random samples. Samples are independent of each other, so the IQ scores are not matched in any way. The three samples are categorized according to a single factor, the blood lead level, low lead, median lead, high lead. So let's test this. So the null hypothesis, mu1 equals mu2 equals mu3. Alternative hypothesis, the means are not all the same. Alpha is 0.05. So you can plug this, do one way ANOVA on this, just like what we did 5 minutes ago. And so we have that the test statistic is 4.0711. The p-value is small. The p-value is 0.0195103.826. So that's, are we testing? Oh, we're testing at 5. So we're testing at 5. And so this is less than alpha. So p is less than alpha. Since p is less than alpha, we are in the rejection region. So the test statistic, so therefore the test statistic is in the rejection region. So we reject the null hypothesis. So it means that not all of the means are the same. So now the question is, well, which one? So on the basis of the ANOVA test, we cannot conclude that any particular mean is different from the others. But if you look here, maybe this one looks different. So maybe this guy here looks different from the other two. I don't know, maybe. Maybe this is the guy that's different. Let's see if we can actually test that. If we can actually, so it appears that the greater blood levels are associated with lower performance IQ scores. Yeah. Okay, so let's see if we can actually do this. So we're going to use the Bonferroni test with the level of significance of 0.05 to identify which mean is different from the others. Okay, so let's do this. So I'm going to just start out the calculation and just sort of finish it off, saying that everything else goes the same. So there's going to be a lot of tests here. So we're just going to more or less show you I'm going to guide you through one of them, and then everything else, will be the same. So first, we need to perform. So there are 3 means here. So there are 3 categories here. Good grief. So there are 3 here. Okay, so we're testing these 3. So it's 3, choose 2. So we're going to have to do 3 differing t-tests. Okay, so we'll have to do the following hypothesis test. Null hypothesis, mu1 minus mu2 is 0. Alternative hypothesis, mu1 minus mu2 is not 0. Alpha is 0.05. I have to divide it by 3, 1/60. And, well, and the other ones. Null hypothesis, mu1 minus mu3 is equal to 0. Alternative hypothesis, mu1 minus mu3 is not 0. Alpha is, again, 1/60. We'll then have to also perform the following t-test. The null hypothesis, mu2 minus mu3 is 0. Alternative hypothesis, mu2 minus mu3 is not 0. And alpha is 1/60. And so let's do the first one. So let me perform this first hypothesis test. Null hypothesis, mu1 minus mu2 is 0. Alternative hypothesis, mu1 minus mu2 is not 0. Alpha is 1/60. Well, we had the following data. And so, here it is. So we have all this data here. And so, let's do that. So I'll just list it down. N1 is 78, X1 bar 102, 0.705128 into 22, X2 bar 94.136364. So the mean sum of squares within is the sum of nu sub I, S sub I squared over nu. Oh, I didn't write down what S was. Let me mark this for a second so I know where to come back. Here it is. Okay. Oh, I guess I actually put in the means there. Okay, so I meant to say paste. Oh, darn. Okay. Oh, what's happening here? Huh. Oh, there, okay. Somehow it disappeared. Okay, 16.8. 15.5. Okay. There. Okay, so we have here S1 is 16.8. S2 is 15.5. Okay. And so to find the mean sum of squares within, you're going to do degree of freedom 77 times 16.8 squared plus 21 times 15.5 squared. I actually wrote out the whole thing here. So, and then 77 plus 21. Okay, so, this is only written out to one decimal, but I did the calculation for actually the raw data. And so you get here 248.42414127. So let's calculate the test statistic. First, let's figure out the parameters for my sampling distribution, the difference to these two sample means. Well, the mean for the sampling distribution of the difference of these two sample means is the difference of the population means, which by the null hypothesis is assumed to be 0. The variance for the sampling distribution of the difference in two sample means is the sum of the variances for the individual sampling distributions, which is sigma sub1 squared over n1 plus sigma sub2 squared over n2. But we're going to approximate sigma sub1 squared and sigma sub2 squared by the mean sum of squares within. And let's factor out, since these are equal, we'll just factor out the mean sum of squares within. And so we'll now use this formula to find the variance, then take the square root to find the standard deviation. And so we get the 248.424127 times 1 over 78 plus 1 over 22, and then take the square root of that to get the standard deviation for the sampling distribution, the difference of these two sample means, 3.8048561705. And so T is equal to X, the difference of their means, minus mu, 0, over sigma, the 3.8, etc., to get 2.252. Your degrees of freedom are, well, if you add up all these sample sizes, it is 118. So if you add up all the sample sizes, so that's going to be 90, 121. So 121, but there are 3 of these. So 121 but there are 3 of them, so it's 118. So with a test statistic of 2.25 and degree of freedom 118, well, the p-value is 0.026172. You adjust this p-value by multiplying it by 3 to get a final p-value of, well, multiply by 3, 0.07856, which is 0.079, which is greater than 0.05. And so that means that our test statistic is not in the rejection region. So we failed to reject the null hypothesis. And so it appears that, we reject the null hypothesis. So it appears that sample ones and sample two do not have significantly different means. And so you keep doing that for the other ones. So if I compare, I compared sample one and sample two, the mean difference, this difference here, was 8.56876. The standard error was the 3.80486. The significance was 0.079. You could actually do a confidence interval and see this, but we didn't do them. So you could have done a 95% confidence interval. But now let's do it between 1 and 3. And you get 0.09, bigger than 0.05. Between 1 and 2, well, between 2 and 1 is the same. So this is going to be, the numbers will be the same, except it's 2 minus, the data for 2 from data, the mean of 2 minus the mean of 1. So that's going to just give you a minus. But everything else is the same. Just changes the sign. 2 and 3. Oh, this is different. So I have 1 and 2, 1 and 3. So 2 and 3 is something different. So if you compare 2 and 3, the mean was negative 0.05411, standard error 4.8. But again, significance is 1, big. Okay, so I have these three, obviously you can repeat it again, these are repeated, instead of here was 2 and 3, we're doing 3 and 2, but these are going to be the same. So in all cases, these are all greater than 0.5, which means that I wasn't able, they all seem to be of the same size. So although ANOVA tells us that at least one of these sample means is different than the others, the Bonferroni test does not identify any one particular sample mean that's significantly different from the others. Okay, so you did all this work for nothing. So we tried to see if we could actually ferret out, from all this, which one, actually had a, was significantly different mean from the others. Our guess was, that the first one mean was different from the others. But once we actually did all the analysis, all of them looked to be the same. This one mean seemed to be the same as the second one. This first mean seemed to be the same as the second one. The second one seemed to be the same as the third one. So all of them seemed to have the same mean. There was not sufficient evidence to actually indicate that this first one was different from, significantly different from these other two. So it's because you have large sample sizes. So okay, so unfortunately, I did all this work. Actually, I did this work, and then just sort of said you can keep doing it, but it didn't help. Let's do the following example. The ages of top executives in 3 major corporations are listed below. Corporation 1, 49 to 62. Corporation 2, 61 to 54. Corporation 3, 56 to 48. Use the analysis of variance at the 0.1 level of significance to determine whether or not the average age of the top executives at these corporations differ significantly. Now, I'm going to do this. So this is the same problem. So it should look familiar. We already did this problem previously. So, right. So we actually already did this problem. So we already did this problem here. And we created a ANOVA table. Now, let's use Excel. So let's use Excel to basically give us all this data. So what I'm going to do is I'm going to input all this data into Excel. Then I'm going to select a add-on package. So hopefully, so you will add on a the analysis toolbox package, and with that, you'll be able to construct an ANOVA table. So if you look here, oops, this is my ANOVA table that I had from before. So this is the same ANOVA table that I had from above. Okay, so let me do that. I did it twice because I like this. So this is the same thing. Oh, and notice they also gave us the critical value and the p-value, so you can compare things. Okay, so let me go and input this data. I've got to look at the data. So let me input all this data into Excel. Oops.
How did you add the package on Excel?
Pardon? Oh, how did I get the package? Yes, yes. I'll show you that in a second. So let me go to.
Thank you.
Let's go to Excel. What the heck is Excel? Oh, 1 second. Okay. Okay, 1 second. Let me go to Excel. Oh, I see. I accidentally closed that. Okay, so let me go back. Here is Excel. Okay, there. Okay, so let me go to Excel. Okay, so okay, so you go to oops, tools. Oh, good, you can see that. And you have Excel. There it is. And so I gotta move this out the way. Oh, you can't see that. That's in the way. Let's bring it down here. Okay, so see where it says analysis toolkit? You just click on that and add it. And it'll take a few seconds to add on. So after a few seconds, they'll add that onto your Excel.
Okay, thank you.
Yeah. Then you never have to do it again. Then it's there forever. Okay, so now oh, let me before I do anything, I have to actually input the data. So let's do corporation 1. Okay, so let's, and then maybe I'll make these a little smaller. Who knows how many cells I need, but okay, so these don't have to be as big. 49, 58, 55, 60, corporation 2, 61, 59, 58, 54, corporation 3, 56, 63, 60, 48. Okay, there. So now let's go to data analysis. So let's go to data analysis, which has been added onto our tools menu. And do ANOVA. So let's do ANOVA and do that. So ANOVA single factor. Input range. Well, let's do my input range. There. So my input range is from A1 to F3. And let's group this by, this is done per row. So the way I've written it across. So I've written it across. Okay. And I have labels in the first column. And alpha is 0.01. And I don't know, I'll want it, I'll put it here. So let's put it down here somewhere. I don't know, I don't care. Let's say right here. Okay, and then say okay. So now, and now it's done. So it's now, so I put it here. Actually, I should put it over here so I could. Oh, well, I should have put it over here rather than here. Okay, so it gives you the summary of all this stuff here. That doesn't look good. So this is the average, the mean, and the variance. Oh, yeah, maybe I should have. Maybe I should actually have made these a little bit bigger so the labels are you can read. Okay, so here are the sum, the average, the variance for each of these. So that's a summary statistic. And here's my ANOVA table. And so here's my ANOVA table here. Oh, I guess. And this is my ANOVA table. So this is the exact same ANOVA table that we got previously when we did this all by hand. And so so Excel has done this all in a fraction of a second for us. So it's kind of nice that it gave us this, and not only that, it also gave us the p-value and the critical value, so we can draw everything out to look nice, and that's it. Any questions about this? Any questions on one-way ANOVA? Okay, so let me go over to let me go back. Oh, yeah. Let me share. Yes, I'm too cheap to buy the pro version. Okay, so yes. Okay, so that finishes off section 12.1. Let me quickly go on to section 12.2. Which is two-way ANOVA. I'm going to try to, let me just check, everything looks fine. Okay, so it's very similar to what we did with one-way ANOVA. It's just the notation is going to be, notation in one-way ANOVA was bad, but once you see the notation for two-way ANOVA, you'll appreciate how easy the notation was in one-way ANOVA. And so the notation is much worse in two-way ANOVA. Okay, so let's do this again. So in this case, we're not going to have just one factor, but we're going to have two factors. Okay, so let's look at the following. Pulse rates with two factors, age bracket and gender. So we have two things. We have an age brackets, and we also have gender. And let's look at the pulse rates. So here are the pulse rates for females between the age of 18 and 29. And let's say ... And let's say males between the age of 30 and 49. So we have all these differing age brackets and these differing gender brackets or genders. So we have age brackets. So one factor is the age bracket, 18 to 29, 30 to 49, 50 to 80. The second factor is gender, female, male. So the question is there interaction between the two factors if one of the factor changes for different categories of the other factor? So let's explore the data with means and an interaction graph. So let's look at my interaction graph. So I have here the average pulse rate for females between the ages of 18 and 29 is 80.4. Between the ages of 30 and 49, 82.2. Between the ages of 50 and 80, 80.4. For males, between 18 and 29, it's 64.8. Between 30 and 49, 76.6. Between 50 and 80, it's 67.2. So the interaction effect. An interaction effect suggests that when line segments are far apart from being parallel, there's no interaction effect if the line segments are approximately parallel. And so it appears that different categories of a variable have the same effect for different categories of other variable. So it does not appear to have an interaction effect. So if I look here for females and for males, well, there does seem to be an interaction effect. Don't know, but it indicates there might be an interaction effect. Well, for age. So it could be that males, interact differently with age as compared with, as a result of their pulse rate, as compared to females. Females are always the same. Okay, whereas males change. Okay, so the objective. So with sample data categorized into two factors, a row variable and column variable, use two-way analysis of variance to conduct the following three tests. So there'll be three tests that we must conduct. First, test for an effect from an interaction between the row factor and column factor. Next, test for an effect from the row factor, then test for an effect from the column factor. So if there is an effect, then test further. And so the requirements for two-way ANOVA. Normality. For each cell, these sample values come from population with the distributions that are normal, variation. The populations have the same variance, sigma squared. The samples are simple random samples of quantitative data. The samples are independent of each other. The sample values are categorized into two different ways. all the cells have the same number of sample values. So if you notice here, all these sample sizes are the same. So the procedure for a two-way ANOVA. First, check for interaction effect. So we begin by testing the null hypothesis that there is no interaction between the two factors. And so F here is the mean sum of squares of the interaction between them, divided by the mean sum of squares due to the error. You reject if the test statistic is small, if it is in the rejection region, if the p-value is small. And so we reject the null hypothesis of no interaction. We conclude that there is an interaction effect. If the p-value is large, we fail to reject the null hypothesis of no interaction between the two factors. We conclude that there is no interaction effect. If there is no interaction effect, then we stop here. If there is an interaction effect, then we should proceed. So if we conclude there is an interaction effect, then we should stop, and we should not proceed with the two additional tests. So if there is an interaction between the factors, we shouldn't consider the effects of either factor without considering those of the other. If we conclude that there is no interaction effect, then we should proceed with the following two hypothesis tests. And so if there is an interaction, then we're done. If there's no interaction, then proceed to look at the rho factor. The null hypothesis. There are no effects from the rho factor. The test statistic is the mean sum of squares of due to the rho factor divided by mean sum of the squares due to the error. Again, you reject the p-value is small. Reject the null hypothesis and no effect from the rho factor. There is an effect from the rho factor. If the p-value is large, then you fail to reject the null hypothesis, no effect from the rho factor. You conclude that you failed to reject. You conclude that it's no effect from the rho factor. Next, you look at the column factor. You test the null hypothesis. There's no effect from the column factor. If the p-value is small, well, you look at the test statistic, the mean sum of squares due to the column factor divided by the mean sum of squares due to the error. If the p-value is small, then you reject the null hypothesis of no effect from the column factor. There is an effect from the column factor. If the p-value is large, you fail to reject the null hypothesis of no effect from the column factor. You conclude that there is no effect from the column factor. So let's summarize the procedure. First, you test for an interaction between the two factors. And so the test statistic is the mean sum of squares due to the interaction divided by mean sum of squares due to the error. If the p-value is small, then there is an interaction effect. If there is an interaction effect, if you reject the null hypothesis of no interaction effect, then stop. You're done. There's an interaction between the two. If instead you fail to reject the null hypothesis that there's no interaction effect, so No. Is there effect due to interaction between the two factors? No. Then you test both the row factor, the F, the test statistic is the mean sum of squares due to the row factor divided by the mean sum of squares due to the error. If the p-value is small, then you conclude that there's an effect from the row factor. You then test for the effect of the column factor. And so the test statistic is the mean sum of squares due to the column factor divided by the mean sum of squares due to the error. If the p-value is small, you conclude that that there is an effect from the column factor. Okay, so let's do the following. Oh, here, wait. Okay, so null hypothesis. There's actually two null hypotheses. H sub OT, mu sub 1, comma, equals mu sub 2, comma, equals mu sub 3, comma, dot, 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 equals mu sub k, comma. Let's call it mu. The other null hypothesis, H sub 0 V, mu sub comma 1 equals mu sub comma 2 equals mu sub comma 3 equal dot, 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 mu sub comma H equals mu. The alternative hypothesis for the corresponding to this, H sub 1T, at least one of the mu sub I commas are different. H sub 1V, at least one of the mu sub comma J's are different. H is the number of columns. K is the number of rows. The test statistic F is S sub T squared over S sub E squared, where nu sub 1 is equal to K minus 1, nu sub 2 is H minus 1 times K minus 1. F sub V is S sub V squared over S sub E squared, with nu 1 equals H minus 1, nu sub 2 equals H minus 1 times the quantity K minus 1. X bar is the sum of X sub I comma J times HK. X sub I comma bar, the sum of X sub IJ over H. We're just summing over the J's. X sub comma J bar is the sum of X sub IJ. We're summing over the I divided by K. X sub T squared is H times the sum of X sub I comma bar minus X bar squared over K minus 1. Again, this is the mean sum of squares, and which is the sum of squares divided by K minus 1. So this is a sum of squares. S sub V squared is K sum X sub comma J bar minus X bar squared over H minus 1. So that's SSV, the numerator, over H minus 1 M sub SSV. Next, S sub E squared is the sum over both I and J of X sub I comma J minus X sub I comma bar minus X sub comma J bar plus X bar squared over H minus 1 times K minus 1. It's SSE divided by H minus 1 times K minus 1. the MSSE. G, the sum of x sub ij over both I and j, the sum of the rows r sub I for I, and this is equal to the sum of s sub j, c sub j, sum of the columns. CF is g squared over n, where n is equal to hk. RSS is the sum of x sub I comma j squared over summing over I and j. SSR is the sum of r squared over the, well, I equal 1 to k. SSC, the columns, the sum of s sub j squared for j equal 1 to h. TSS is RSS minus CF. SST is SSR over H minus CF. SSV is SSC over K minus CF. SSE is TSS minus SST minus SSV. Okay, so let's do an example. Pulse rates. Given the pulse rates from the earlier table, use two-way analysis variance for an interaction effect, an effect from the row factor of the age bracket, and effect from the column factor of gender. Use a 0.05 significance level. So, requirement check. So I have here that for each cell, the sample values appear to be from population with a distribution that's approximately normal. Again, looking at your normal quantile plots. The variance of the cells, 103 to 293. So 51.7 to 293.5. Differ considerably, but the test is robust against departure from equal variances. So we're not too concerned about that. The samples are simple random samples. Samples are independent of each other. The subjects are not matched in any way. Sample values are categorized into two ways: the age bracket and gender bracket. All the cells have the same number, 10 sample values. So all the requirements are satisfied. And so let's look at my ANOVA table. So I just sort of gave you the ANOVA table. And so step one, the interaction effect. So we began by testing null hypothesis. There is no interaction between the two factors. And so the test statistic for the interaction is F is the mean sum of squares due to the interaction divided by mean sum of squares due to the error. So the mean sum of squares, so the sum of squares due to the interaction was 272.5333, and the degrees of freedom for the interaction was 2. So take this number. Usually most people do it this way, that this is the third column and this is the second column. So usually they put the degrees of freedom here so that you, I don't know, stack crunch is weird. Usually it's done over here. Okay, so it's the 272.533 divided by 2 gives us the 136.266. And the mean sum of squares due to the error is, well, the sum of squares due to the error, 7836 divided by the degrees of freedom 54 gave us the 145.111. So you take the ratio of these and you get, so take the 136 divided by 145 to get 0.9395054, which is gigantic. So that's a pretty big number. So the p-value here is 0.3973. So that is not in the rejection region. So you do not reject the null hypothesis of no interaction. Okay, so there does not appear to be, so does not appear that pulse rates are affected by this interaction between the age bracket and gender. There does not appear to be an interaction effect. Okay, good. So now we have to proceed. So now let's proceed. Because there does not appear to be an interaction effect, we proceed for the test of the effects from the row and column factors. And so the hypothesis test. There's no effects from the row factor. Okay, so let's test this hypothesis, and obviously the alternative hypothesis that there is an effect from the row factor. Okay, so let's look at the row factor. And so F is equal to, let's look at the row. Now I forget which is row. Row is age. It was, yeah, rows were the ages, and up here were the genders. So this is the row. So this is my row. Actually, I should say that here. This is my row. Here's my row and column. Okay, so so my row was the mean. I'm sorry, the sum of squares was 526 divided by 2 gives me the 263.466. Let's see, row. There it is. Divided by, again, the error, 145. And so you take this number divided by this number to get 1.8. So I took the 263 divided by the 145 to get the 1.8. The corresponding p-value is very large again. It is greater than alpha, which was 0.05. And so this is greater than alpha. There it is. Greater than alpha. I should have put the alpha here somewhere. It's greater than alpha, which is 0.05. So that means that we are not in the rejection region. So we failed to reject the null hypothesis of no effects from the age bracket. So there does not, so pulse rate do not appear to be affected by the age bracket. Okay, so now let's look at the column factor, which was gender. Oh, they actually tell it there. The column factor is gender. And so let's look at the column factor. And so the sum of squares was 1972 divided by 1 is still 1972. Okay. Then you take the 1972 divided by 145 to get the 13.5. Okay, so the mean sum of squares for gender was 172.266. The mean sum of squares for the error was 145.111. And so I get a 13.591424.196. The p-value is small. So since the p-value is smaller than 0.05, then that means that the test statistic is in the rejection region. So I reject the null hypothesis. So I reject the null hypothesis of no effects from gender. So pulse rates do seem to be affected by gender. So on the basis of the sample data, we conclude that the pulse rates appear to be affected by gender, but not by age bracket and not by the interaction between the age bracket and gender. Any questions about that? Okay. So
actually, you have a sample of that sample. Pardon? Do you have that sample on the Excel? I just wanted to see how the rows look like.
Oh.
No, if you have it.
So do
If
I?
you don't have it, it's fine.
No, well, yeah, I'd have to put in all the data.
Okay.
And do I have? I don't have the data here. I didn't input the data. Yeah, I didn't put in all the data here. I'd have to input. I'd have to input all this data,
Yeah.
which is a lot of. So the answer is, I'd have to do it. I'd have to do all that data, which is just a lot of data to input. So the answer is no. I didn't input all this data. But yeah, you'd have to input all that data to do two-way NOVA.
Because
Okay.
the
Yeah.
issue, at least in my mind, when I am looking at the age, and then I see, let's say, only
Right.
the female, do I make the age for each one of them, or it's just independent?
Right. Yeah. So I guess what I'll do is after this. So not right now, because there's a lot of data input. I'll input all the data. So let's remember. So I'll remember to do that. I'll input into Excel. Okay, so I'll input that into Excel, and I'll maybe I'll do it as a little attachment. So I'll attach it also to section 12.2. I'll attach that with instructions on, I'll show you how to input it into Excel, and I'll make that as an attachment to section 12.2. Okay, so
Okay.
I'll input it and then attach it.
Okay,
Just because it'll take a second. It'll take actually a few minutes to input all this data. Okay, so that finishes off chapter 12. Let's go on to chapter 13. But let's have a break. So let's have a break here until 10:30. So let's have a break until 10:30. And during the break, let me answer your questions. So let me answer. Let's see if they had any more than those. You only had those two. So let me answer these two questions. So while everyone's on the break, let me answer these. Oops, which is not that one. Okay, so let me do this. Let me do this. Okay.
Question, Professor.
Yes, question.
So let's say, because we still have a lot of assignments to due. Well, actually, I have assignments that I haven't started yet. So I was wondering at the end of the class, like, it's on June 6th, or when it's the last day? Oh, sorry. Okay, we can.
It is. It is.
I just want to make sure what's the last day that we can turn on the assignments.
June. Right. So June 3rd. So June 3rd is the last day of class.
Okay.
So June 3rd is the last day of class, but you can still do assignments up to June 5th.
Okay.
But and if you do anything past June 5th, because I've got to get everything submitted by June 9th. So if you do anything past June 5th, you can still do it, but you'd have to email me saying that you did it so I can recalculate scores. So if you do it past, so up to June 5th, everything's okay. You can do anything you want. After
Okay.
June 5th, tell me that what you've done, so I can look at that part. Say I did more Canvas work or homework or something, or I did more stat, my stat lab. So I'll recalculate. I'll put in the new data. Okay. So
Okay.
just be sure that if you happen to do something past after midnight on June 5th, that you tell me that. Okay. So that I know to recalculate in case I've already input into my spreadsheet, that I should recalculate things. Okay.
You said that on Wednesday we're gonna take the exam 3, right?
Exam 3 is on Wednesday. So exam 3 is on Wednesday, June 27th. Okay. 29. I'm looking at 29.
We're 20. It's
June
27.
20. May 29th. Whatever. I'm wrong day. I gave you completely wrong information. On Wednesday, May 29. Wednesday, May 29. I'm sorry.
So since we since we joined the class meeting today, so we get points for homework.
You get points for you're taking lecture notes during this. And you will attach your PDF of the lecture notes to, if you look in the announcement, it tells you where to put the lecture notes. And
it's on announcement.
Yeah, and if you click on that, there's a place to put your file. So you take as much lecture notes as you can, and you will attach that. Okay. Okay. So let me do this now.
I have a question. Hi, good morning.
Yes. Oh, yes.
So just to avoid confusion, you're talking about a different school with the gal that you were confirming testing dates for, correct?
Oh, yeah. I'm sorry. That's for the Monday through Thursday morning class. Yeah.
Okay.
That's for the late. There's a late start class. There's a late start class. I teach you more than one statistics class. Yes. So that does not involve you.
Okay,
so
thank you.
That is not for you. Sorry about that.
No, not at all. I'm Saturday class here.
Right. So that's not at all the Saturday class. Okay. So. Okay, and then I have to do this and that. Okay. So let's copy this guy. Also, okay, so and then we'll.
What time does the meeting end today?
It ends when we're done with chapter 13. So whenever we're done with chapter 13, it probably will be a little bit before 2. So my guess is around 2 o'clock. Okay, so
let's say if we leave the meeting, is that fine?
Yeah. So you can always look at. So what you would do is you would go to the taping of this, recording of it, and you would then just do the lecture notes completed from that. From that particular, from you watching the video. Okay.
So today the meeting is, because I'm just looking right now, the extra credit chapters 12 to 13. So it shows it's gonna be 8 to 2 p.m. So
right,
because I cannot stay until 2.
Right.
So is it okay if I?
Yeah. So you can. Yeah, so you just leave and you would then watch the recording. Okay, so you just watch the recording of it and take the lecture notes from the recording
for a moment, and then I'll come back later, like in an hour. Is that fine too?
Yeah, that's also fine. And you can also pick up whatever you missed by looking at the recording. Okay, so let me do this. Managers rate. 5 minutes. Managers rate employees according to job performance, attitude. Results from several randomly selected are given below. Use the given data to find the linear correlation coefficient. Okay, so I have here that R. Well, oops. Let me put in the data. X, Y. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Okay. 5, 6, 4, 8, 9, 9, 5, 8. Okay, so let's input your data. And so let's do XY, X squared, Y squared. Okay, so let me input my data. Let's see if possibly if I can do it on this. Let me just check correlation coefficients. Okay, so let me just check. Okay. I'm just gonna check something. What the heck? Okay, big fingers. Let's do it with this guy. Let me just check something. Oh, you stopped that. Okay. It does give it. Okay, so let's quit that out. Okay, so let me input the data. So 1, 6, 7, 9, 3, 1, 6, 4, 4, 1. Let's store that in L1. Next, store 5, 6, 9, 4, 2, 8, 9, 9, 5, 8. Store that in L2. Okay, good. And now, oops. Let me do, oops. L1, L2, store that in L3, L1 squared, store that in L4, L2 squared, store that in L5. Okay, so now, let me go to edit. Okay, so now let me just put in all that data into my table. And so let me do that. And so 1, 5, and so that's 5, 1, 25, 36, 36, 36, 63, 49, 81, 36, oops, 81, 16, 6, 9, 4, 8, 1, 64, 54, 36, 81, 36, 16, 81, 20, 16, 25, 8, 1, 64. Okay, good. Okay, so I just basically read off all of that stuff there. Okay, so now let me do the sums. Okay, so let's quit. Let's do stat calc. Two of our stats, L1, L2, good. Okay, so here's all this other stuff. The sum is 42. Sum of x squared is 246. N is 10. I just list that somewhere. The sum of y is 65. The sum of y squared is 477. The sum of xy is 272. Okay, good. Let's get rid of this for a second. Okay, so I have r is equal to n sum xy, sum x, sum y over radical n sum x squared minus sum x squared n sum y squared minus sum y squared. Okay, so r is equal to 10. So now I'll just plug in all these numbers here. Ten, 272 minus 42, 65 over radical 10 sum of x squared 246 minus sum of x 42 squared square root of 10 sum of y squared, so 477 minus sum of y 65 squared. And now, lastly, so it looks like I did all this calculation, but I just input it to the calculator. So now here, let's go to stat, calc, linear regression, I guess. I'll do linear regression, L1, L2. And I get R is a negative 0.01623666762 rounded to the nearest thousands. And that's your answer. Okay. Okay. Then I guess on the next break, I'll do the other one, which is actually, I can do that since I have all the data there. Since I have all the data, I can actually figure out the test statistic. And so my test statistic, I'm assuming this is all the same data. No, it's not all the same data. Okay, so I'll do this next time. So I'll do this in the next break, I guess. So, okay, so I'll have to do that in the next break here. Okay, so let me continue with chapter 13. Okay, so let me continue with chapter 13. Oh, and I think there's some more there. Okay, so I'll have to also do this one. Copy. Regression line, okay. The slope, so same thing. Oh, into the slope. No, that's the same question. Sorry, that's the same question. Okay. Slope, then this one. Here. And then this one. Okay. Oh, that's a nova. Okay. Okay, so let's go on to, okay, so I'll answer those in the next, during the next break. Okay.
Professor, I have a question.
Yes.
So for the group work, I just saw, I
Mhm.
was doing it on the Google Docs, right? For the group work.
Mhm.
So is it okay if I do it on the Google Docs, or it has
Sure.
to be hand? Yeah. Okay.
Yeah, you can do it on Google Docs if you wish to type it in. Okay.
Okay. Thank you.
Okay, so chapter 13, non-parametric tests. Section 13.1, basics of non-parametric test. And so up to now, we've been mostly using parametric test. A parametric test is a test whose model depends upon certain conditions about parameters of a population from which the samples are drawn. And so, we're assuming that the mean is equal to 7 or something, or the variance was equal to 12, or the population proportion was equal to 0.5. So we're making some assumptions about the parameter. Many parametric tests, in addition, have a requirement about the distribution of the population, assuming that the population is normal, or binomial, or hypergeometric, or something of that sort. Which is, so a non-parametric test. A non-parametric test does not make assumptions about a particular value of a parameter. And so they don't assume that the population mean is 22 or something. A distribution-free test does not depend upon the particular form, the basic frequency distribution from which the samples are drawn. So we're not assuming that the population is normal, or that the population is binomial or hypergeometric. And so that's called a distribution-free test, which is different than a non-parametric test. And so a distribution-free test does not require samples to come from populations that are normally have normal distributions, or particular distribution, any particular sort of distribution. Now, misleading terminology. So unfortunately, the term distribution-free test correctly indicates the test does not require a particular distribution. The term non-parametric test is misleading in the sense that it suggests that the tests are not based on a parameter. But many non-parametric tests are based on an assumed value for a parameter, such as the median. So even though they're called non-parametric, they actually assume that the population median is equal to 0.5. So they're actually not non-parametric. So non-parametric means that you don't assume a value of a parameter. However, since people call these non-parametric tests, even though they aren't their parametric tests, we will still call them non-parametric tests. And so due to the widespread use of the term non-parametric, we'll use that terminology. But again, tests that does not require a non-parametric, a particular parameter from a distribution is called non-parametric. All other ones are called parametric. However, we sort of let that definition, loose, and we just sort of disregard the definition. If people had previously called it, if everyone calls it non-parametric, I'm a lemming and I jump off a cliff. I don't care. Everyone else is jumping off the cliff. I will follow them over the cliff. And so if everyone else calls it non-parametric, even though it is parametric, we will still call it non-parametric because everyone else calls it non-parametric. And that's just, well, and similarly, people confuse the fact that sometimes they call a distribution-free test a non-parametric test, which it is not. It's a distribution-free. So even though that's why we actually include distribution-free in non-parametric tests, because a lot of people call distribution-free tests as non-parametric. So this aside, what are the advantages of a non-parametric test? So the advantage of a non-parametric test is that it can be applied to a wide variety of situations because you do not have to require these more rigid requirements of that, for the corresponding parametric method. In general, non-parametric methods do not require that we are sampling from a normally distributed population. Many non-parametric tests are, distribution free. Non-parametric tests can be applied to more data types than parametric tests. So unlike parametric tests, non-parametric tests can often be applied to categorical data, such as genders of the survey respondents. Non-parametric tests can be used with data that consists of ranks. This is, the first, the top, the fourth, the third person, the top, the third category, whatever. So they can be used with all of these ranks. What are the disadvantages? So that's a lot of, so it's can be used in many, many more situations than parametric tests. What are the disadvantages? Non-parametric tests tend to waste information because exact numerical data is often reduced to some qualitative form. So even though, I have the exact timing that you took to complete the race, I only say that you came in third place. So we throw out many times, not always, but most times we throw out information. Non-parametric tests are not as effective as parametric tests. So a non-parametric test generally needs stronger evidence, such as a larger sample size or greater differences to reject a null hypothesis. And so most times the null hypothesis will not be rejected when you do a non-parametric test. And so there's usually not enough statistical evidence to reject the null hypothesis. Just because you need a lot of evidence to actually reject your null hypothesis when doing a non-parametric test. So the efficiency of a non-parametric method. So suppose we have some situation, say matched pairs of sample data. Is there a parametric test that's available? Yes, there's a t-test that's available. Is there a non-parametric test that is available? Yes, there's actually two differing non-parametric tests, a sign test or the Wilkinson sign rank test. Now, the efficiency rating of non-parametric tests with normal populations. So suppose we have matched pairs drawn from a normal population. So I've matched up, so we have these normal populations, and we matched up these pairs. We then conduct a t-test of a certain sample size. We then conduct a sign test to get the same level of significance for this sign test as compared to a t-test. I need, well, let's do it the other way. For a non-parametric test, I only need 63% of the sample size that I would need for a sign test to get the same level of significance as the sign test. So my efficiency rating is that the sign test is only 63% as effective as my t-test, because the t-test would only need a sample size of 63% to get the same, to have the same confidence in my hypothesis test as my sign test. For the Wilkinson sign rank test, it's 95%. For two independent samples, I have a t-test. I have the Wilkinson rank sum test. By the way, this is always confusing. This is Wilkinson signed rank test. This is rank sum test. So it's a rank signed ranks is not the same as a rank sum test. They both have rank in it. They both have Wilkinson, but one is sum, the other is signed. So the Wilkinson rank sum test is efficiency of 95%. Three or more independent sample, we have ANOVA. We have the Kruskal-Wallis test, 95% efficiency. Linear correlation, we have the rank correlation test, 91%. Even though it tells you a little bit different information, but randomness, there is no test, no parametric test. And so there is the runs test. So there's no basis for comparison. Okay, so let me tell you about rank. Okay, so data are sorted, according to some criteria, such as smallest to largest, best to worst. The rank is a number assigned to an individual sample item according to its order in the list. So the first item is assigned a rank of 1, second a rank of 2, so on. So how do I handle ties? So let's see, how do I handle ties among ranks? So we have the following numbers: 4, 5, 5, 5, 10, 11, 12, 12. So the rank is, first, so let me do a preliminary ranking. So, this is the smallest. So ranking is 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8. But that's not fair. This 5 is the same as that 5. So these 5s are all the same. They should be all given the same rank. So how do I find the rank? When they're ties, I give the mean rank. So this 4 still has a ranking of 1, but each of these 5s will have a ranking of, 2 plus 3 is 5, plus 4 is 9, divided by 3 is 3. So each of these 5s will have a rank of 3, the average of the 2, 3, and 4. the 10 still has a ranking of 5. The 11 still has a ranking of 6. But now the 12s, again, it's not fair that one 12 has a ranking of 7, the other has a ranking of 8. So we give them both the average ranking. So 7 plus 8, 15 divided by 2 is 7.5. So each of these 12s would be given a rank of 7.5. And those are my rankings for each of these numbers. Any questions about that? Okay. Okay, good. So I finished this off, section 13.1. Let me go on to section 13.2. Section 13.2, sign test. And so the sign test is a non-parametric test that uses plus and minus signs to test claims involving matched pairs of sample data. So for matched pairs, you subtract the second value from the first, record the sign, and you ignore any zeros, anyone where they're the same number. Claims involving nominal data. And so you represent each number of one category with a positive sign and each member of the other category by a negative sign. Claims about the median of a single population. Subtract the median from each sample value and record the sign of the difference. And again, you ignore any zero. So if any of the sample values are equal to the median, you disregard those. So the basic concept of the sign test is that to analyze frequencies of the plus and minus signs to determine whether they are significantly different. And so if you're using a table, then again, you're going to do a right tail test. Then you would, the test statistic would be based on the number of times that the less frequent sign occurs. I'll usually try not to use the tables so that I don't have to make that assumption, because it's actually kind of confusing for students. Okay, so requirements. The sample data are a simple random sample. That's it. So there are no other requirements, such as it has to come from normal population or whatever. It's just that it's a simple random sample. That's it. The median is denoted by eta. Let X be the number of times the sign occurs. If you're looking at a table, then the table will be you'll have to use a left tail test, in which case X will be the value that occurs less frequently. Let N be the total number of positive and negative numbers combined, meaning it's a sample size, but you take away all of the zeros of X minus eta. If N is large, then we can use the normal approximation with continuity correction. So then the sampling, then I have that X is approximately binomial with sample size N and with, probability of success 0.5. We'll replace X by X plus 0.5 if X is less than N over 2, and X minus, we'll replace X by X minus 0.5 if X is greater than N over 2. So note that the second case will never occur if we let X count the number of less frequent signs. Okay, so when applying the sign test using the less frequent sign on a one-tail test, we need to be very careful to avoid making the wrong conclusion when one sign occurs significantly more than the other, but the sample data contradict the alternative hypothesis. So I will usually not restrict the test to be the one less frequent. So this type of wrong conclusion is avoided. And so, for example, suppose, so if you use the table, then you have to be concerned about the following. And so among 945 couples using the XSort method of gender selection, 66 had boys. So the sample proportion of boys is 66 out of 945.0698. This is on data from Genetics and IV Institute. Consider the claim that the XSort method gender selected increases the likelihood of baby boys. So the probability of a baby boy is greater than 0.5. So the claim P greater than 0.5 becomes the alternative hypothesis. So if I look at the sample proportion of boys, it's 0.0698, which can, this can never support a claim that this value is greater than 0.5. So this contradicts the alternative hypothesis because it's not greater than 0.5. The sign test shows that 66 boys in 945 is significant. So it is significant. So meaning that we reject the null hypothesis. So I reject the null hypothesis. So, quote unquote, this claim is supported. But it's not. So if you looked in the table, you would see that, yes, this is significant. 66 out of 945 is significant. But it is significant in the wrong direction. So even though you would think it would say that we support this, but it's impossible. We can never support this. So you have to be careful to say that, no, actually, even though it says it's significant, it actually doesn't contradict the null hypothesis. And so, 1 second. There. Okay. Next, a leading tire manufacturer introduces a new tire with a median life expectancy of more than 60,000. Independent agency tested a random sample of 8 such tires, recorded the number of miles in thousands that the tire lasts, 62 to 57. Used a sign test at the 5% level of significance to test the manufacturer's claim. And so the requirement of the sign test is sample data is a simple random sample. So this is satisfied because you have a random sample. So my hypothesis test is, well, let's see, more than 60,000. So that's the claim, is that the median is more than 60,000. I'll do everything in terms of thousands because they give the data in terms of thousands. So the median is more than 60. No equal sign, so that will be the alternative hypothesis. So null hypothesis, eta is less than or equal to 60. Alternative hypothesis, eta is greater than 60. And let alpha equal 0.05. So let's put down pluses and minuses. So if you are greater than 60, it's a plus. So plus, plus, minus, minus, plus, equal, get rid of, plus, minus. So I get rid of the ones where it's not greater than, it's equal to, where I get rid of the ones that are equal to 60. And so I have here 1, 2, 3, 4. So 4 are greater than. Okay. So I have here that 4 are greater than. Let's find the critical value. So n is equal to 1, 2, 3, 4, 5, 6, 7. So n is equal to 7. I want to find the probability x is greater than or equal to 7. I could look on my binomial. So there's two things here. So it's a binomial, success or failure. And so I could find the probability x is greater than 7. And so 7c7, 0.5 to the 7, 0.5 to the 0. Again, there's a 50% chance of success and a 50% chance of failure. So 0.0078125. Let's find the probability x is greater than or equal to 6. And so 7c7 times 0.5 to the 6 times 0.5 to the 1 plus the previous value we just did. So 7c7 0.5 to 7 times 0.5 to 0, 0.0625, which is too big. So 7 is not big enough. 6, 7 above is not big enough, but 6 and above is too big. And so our rejection region is here at the 7, where alpha is only equal to 0.007825. But let's look at 4. Well, the critical, so my test statistic here is 4. This is greater than, so there are 4 pluses. So I do not reject the null hypothesis. Basically, notice virtually everyone had to be greater than 60. You had to have 7 of the 7 be greater than 60 in order for us to have enough, in order for us to have enough data to reject the null hypothesis. So it's really hard to reject my null hypothesis. And usually that's what happens with these non-parametric tests, that it's really difficult to reject my null hypothesis. So I do not reject the null hypothesis. So no, there's insufficient evidence to support this leading tire manufacturer's claim that this new tire has a median life expectancy of more than 60,000 miles. Again, because this sign test here, it's really difficult to reject the null hypothesis. Test the hypothesis that the median life of a new brand of tire is at least 48 months. A random sample of 33 tires revealed the following tread lives in months. So 39 to 48. Use alpha equaling 0.01. So again, the requirement of the sign test that the sample data is a simple random sample. Okay, good. The requirement is satisfied. Hypothesis test is median at least 48. Oh, that's a null hypothesis. So the null hypothesis says that the median is greater than or equal to 48. Alternative hypothesis says the median is less than 48. And alpha equals 0.01. Okay, so I guess I'll get rid of the one that's equal to 48. Good. So I got rid of the ones that were equal to 48. I guess I just made the ones less than 48. I made those red. So the ones that were less than 48, I made those red. All the other ones, the black, are greater than 48. Yeah, the black are all greater than 48. Okay, good. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 27, 28, 29, 30, 31. So n is 31. P is a half. Let me use the normal approximation to the binomial distribution. And so let's check if the normal approximation is applicable. And so I have here 31 times 0.5, 15.5. In Q, 31 times, if there's a 50% chance of success, there's a 50% chance of failure. 15.5, also greater than equal to 5. So yes, the normal approximation to the binomial distribution is applicable. Let's do continuity correction. And so 11 is less than 15, so I subtract. So 11 minus 0.5, 10.5. Let's figure out the parameters. And so mu is equal to NP, 31 times 0.5, 15.5. Sigma is equal to radical NPQ. So radical 31 times a half. Again, if there's a 50% chance of success, there's a 50% chance of failure. So 2.7833218. Let's find the critical value. And so critical value for the normal distribution. This is going to be left-tailed 0.01, negative 2.326. Again, you can look at the table or use your inverse norm, etc., etc. We've done this a million times, or you just remember this value. And so let's calculate my test statistic. Z equal x minus mu over sigma. So 10.5 minus 15.5 over 2.7838818, negative 1.79605321, which is my test statistic, is not in the rejection region. So I do not reject the null hypothesis. So I did not reject the null hypothesis. So actually, in this case, yes, there is insufficient evidence to reject the claim that the median life of a brand new tire is at least 48 months. Okay, so now let's do match pairs. And so, is there a gender difference in ages between best actresses and best actors? And so, the table lists the ages of Oscar-winning best actresses and ages of Oscar-winning best actors. The ages are paired according to the year the awards were presented. Use a sign test with sample data testifying that there's no difference between ages of best actresses and best actors. Okay, so let's do this. So I have here, well, best actress is younger, so negative. Older, positive. Younger, negative. Older, positive. Younger, negative. The same, get rid of. Younger, negative. Younger, negative. Younger, negative. Younger, negative. Okay, so the only requirement for the sign test is that we have a simple random sample. We'll assume that this is a simple random sample. So that requirement is satisfied. And so the hypothesis test. The null hypothesis that eta sub d is 0. There's no difference. The median of the differences is equal to 0. So the median ages are the same. The alternative hypothesis, mu sub d is not equal to 0. There is a difference. The median of the differences is not equal to 0. Alpha is equal to 0.05. So my test statistic is, well, let's see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9. So n is 9. And in this case, it doesn't really matter. Either I could do 2 or 1, 2, 3, 4, 5, 6, 7. So I could either let x, because it's two-tailed. So I could either let x be 2 or 7. I'll let x equal 2 because it's the smaller one. So the number is the number of the less frequent sign. Okay. So I can look in the table. So I'll just look in my table. Because in this case, it's two-tailed. Since two-tailed, doesn't matter which one I pick. So I'll pick the smaller one. The sample data doesn't contradict, the alternative hypothesis that they're, not equal to 0. So there is a difference between 2 positive signs and 7 negative signs. So there, I certainly it seems to be different to me. So the sample data show difference. Okay, so let's determine if this difference is significant. So I can find the critical value. So n is equal to 9. And so I can refer to the table with a critical value of 1 when n is equal to 9. So the critical value here is 1. The other critical value would be 8. It is, again, two-tailed. So n is 9 and alpha is 0.05 and it's two-tailed. Well, my test statistic is 2. So my test statistic is not in the rejection region. So we failed to reject the null hypothesis. So we do not reject the null hypothesis. So there is insufficient statistical evidence to reject the claim of no difference between the ages of best actresses and best actors. So even though it was a lot, again, it takes a lot to actually, not, to reject the null hypothesis. So you have to have a lot of evidence to reject your null hypothesis. Table 13.3 includes taxi out times, taxi in times for a sample of American Airline Flight 21. The sign test. Use the sign test to test the claim that there is no difference between taxi out and taxi in times. Use a 0.5 significance level. Okay, so again, we'll assume that this is a random sample. So the requirement is satisfied. We have, so let's see, get rid of this guy. This is, I'll take the first, I'll look at the first one as greater. And so plus, minus, plus, minus, plus, minus, plus. Okay. And so I have here 1, 2, 3, 4, 5, 6, 7, 8 plus signs, 1, 2, 3 negative signs, and then get rid of the 0. There's 1 0. Okay, so in here is 11. And let's test if there's no difference. Again, it's two-tailed. So I'll take the smaller one. So the smaller one is 1, 2, 3. So X is 3. So the null hypothesis, there's no difference. The median of the difference is 0. The alternative hypothesis, there is a difference. The median of the differences is not equal to 0. Alpha is equal to 0.05. And so n is 11. I had to get rid of this guy. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. N is 11. Alpha is 0.05. Two-tailed. And so the rejection region only consists of 1 and 11. So my test statistic is 3. Well, you could either do the other one. You could either say 3 or 8. But either case, it's either 3 or 8. But if I make it a 3, it still is not in the rejection region. Therefore, we do not reject the null hypothesis. And so, yes, there's insufficient evidence during the rejection of the claim of no difference between taxi out times and taxi in times. So again, it's really hard to reject your null hypothesis. Any questions? Okay. Use the classical method of the sign test to test the null hypothesis that A to 1 is equal to A to 2. A researcher gives a new feed to a randomly selected sample of 6 cows and records their weights before and after experimental period as follows. No wonder there's such large numbers. These are cows. Okay, so use a sign test at the 0.05 significance level. Test researchers claim that new feed is effective. Oh, it's one-tailed, increasing the weight. Okay, so I have here, then again, this is the claim that null hypothesis A sub D is less than or equal to 0. Alternative hypothesis A sub D is greater than 0, alpha equals 0.05. Okay, so I guess I'll do the after, because we want to gain weight. So we wanted to gain weight. And so this is plus, minus. Oh, actually, I should put, oh, here, it's right here, plus, minus. Lost weight again, minus, plus, minus. Okay. So, n in this case is 3, 4, 5, 6. And x, I don't care, x is greater than. So x is plus. There are 1, 2, 3 pluses. One-tailed, 0.05, n is 6. We get a critical value of 6. Therefore, this test statistic is not in the rejection region. Since the test statistic is not in the rejection region, we do not reject the null hypothesis. So no, there's insufficient statistical evidence to support the claim that the new feed is effective in increasing the weight. Claims involving nominal data. So let's do an example. Gender selection. The Genetics and IV Institute conducts a trial of its method of gender selection for babies. Before the clinical trial, we were concluded 879 of 945 babies born to parents using the XORT method gender selection were girls. Use a sign test and a 0.05 significance level to test claim that this method of gender selection is effective, increasing the likelihood of a baby girl. Okay, so okay. I changed it from girls to boys. I don't know why. It doesn't really matter. Oh, okay, so I did in terms of boys. So let's do, again, this is a simple random sample. And so let P denote the number of baby boys. So I'm going to do baby boys. So even though they're saying girls, I'll do boys, only because I did boys down here. Okay, so the null hypothesis. So I want girls to be more likely, which means that boys are less likely. So the alternative hypothesis is that P is less than 0.5. The null hypothesis, P is greater than or equal to 0.5. Alpha is 0.05. Again, this is actually the more likely way that I would have done it. But then I wrote a comment where I then did X's as being boys. Okay, so let's denote girls by, I should have had these as girls as being Oh, this is less than 0, so that's negative. So yeah, girls is being positive. So I have girls as being positive and boys as being negative. So I just arbitrarily pick girls as positive, boys as negative. We have 879, 879 positives. The others, 945 minus 879, are negatives. And so 66 were negatives. I'll assume that you can't have both a boy and girl. The child is not a boy and girl. So so there's no duplicates there. The sample data does not contradict the alternative hypothesis because the proportion of girls is greater than 0.5. The proportion of boys is less than 0.5. I changed it here, but not there. Okay. We can check if the normal approximation is applicable. And so NP, 945 times 0.5 is 472.5. NQ, 945 times 0.5, 472.5, greater than equal to 5. So yes, the normal approximation is applicable. And then we also have continuity correction. The 879 was greater than. It should actually be, doesn't really matter. So with continuity correction, this should be 879. Okay, so the 879.5. Okay. Oh, I see. But I'm doing it as boys. I'm doing it as boys. I'm doing it as boys. I forgot I'm doing boys. So as boys, it's 66, which is less than. So it's 65.5 minus mu, which is 495 times 0.5 over sigma, which is the square root of NPQ. And so I get a negative. So in this case, I'm going to get a negative. So I get a negative 26.414361.945, which is in the rejection region. So I reject the null hypothesis. Okay, so yes. So I rejected the null hypothesis. So it's less than. So there's less than 50% boys or more than 50% girls. And so, yes, there's insufficient evidence to support the claim. Yes, there is sufficient statistical evidence to support the claim that girls are more likely with the XOR method. Body temperatures. And so we use 106 temperatures listed for 12 a.m. on day 2 with a sign test to test the claim that the median is less than 98.6 degrees Fahrenheit. Of the 106 subjects, 68 had temperatures below 98.6, 23 had temperatures above 98.6, 15 had temperatures equal to 98.6. We'll get rid of those guys. Based on, we'll assume that the sample data are simple random sample. The hypothesis test is that the median is greater than or equal to 98.6. The alternative hypothesis that the median is less than 98.6, and let's say alpha equals 0.05. Let's see if my normal approximation is applicable. So n times p. So this is 68 plus 23 is 91 times 0.5. N times q, 91 again, if there's a 50% chance of success, it's a 50% chance of failure. So again, 45.5. So yes, both NP and NQ are greater than or equal to 5. Let's do continuity correction. I guess I'll do the ones that are above. And so I get a 23.5. And let's find the mean, NP, 91 times 0.5. Sigma, NP, radical NPQ, radical 91 times a half. And so I get Z equals X minus mu over sigma, the 23.5 minus the, 45.5 divided by the square root of 91 over 4. And so I get a negative 4.6, 1.24532.816. Your test statistic is in the rejection region, so I reject the null hypothesis. So yes, there's sufficient evidence to support the claim that the median body temperature of healthy adults is less than 98.6, is not equal to 98.6 is commonly believed. Any questions on section 13.2? Okay. Section 13.3. The Wilkinson sign rank test for matched pairs.
Professor,
So, yes, question.
sorry. So for the notes, how many notes do we have to take to get the extra credit? That's one of the questions I have.
Well, so the more
can
you
we just
do,
put like
the more. So
Mhm.
So I grade you on the amount of lecture notes and the accuracy of your lecture notes. So I can give you up to 15 points. Today is for homework. So if 15, I would add 15% to your overall, up to 15% to your overall homework average. As you know, as calculated at the end of the semester. So the more lecture notes you have, and the how accurate they are, will give you more and more of those points. Okay.
So
you
yeah,
can, right. So if anything is missed, you can look over at the recording to grab anything that you missed, and also you can look at the PDFs in Canvas. You can look in Canvas for anything that you sort of missed that we covered. Okay.
Okay.
So you have several sort of ways to look at it, and you have till tomorrow night to turn those in.
Oh, okay. Yeah, because right now I'm just trying to know. I just want to know how many do we have to have in total, or like what's the limit? So I'm
Right.
gonna to get the points because I do need the extra
Right.
credits. Yes.
So it's the closer they are to what I've covered, the more points you get is the
Okay.
answer. Okay.
Okay.
Okay then. Okay, so the Wilkinson sign rank test involves the conversion of sample data into ranks. So we can test it for the following. Test a null hypothesis of the population of matched pairs has a difference with a mean equal to 0. So we're testing a claim that the population of matched pairs has a property that the matched pairs differences has a mean equal to 0. Or we can test a claim that a single population of individual values has a mean equal to some claim value. Okay, so for matched pairs, the null hypothesis would be that the matched pairs have differences that come from population with a median equal to 0. Alternative hypothesis would be matched pairs have a difference that come from population with a non-zero median. For the other case, you would test the claim that the population has a mean equal to some claim value. The alternative hypothesis would be that the mean is not equal to that claim value. The requirement are that the matched pairs are randomly selected, and looking at the population differences found from the pairs of data, that this has a distribution that is approximately symmetric, meaning the left half of if its histogram is roughly a mirror image of its right half. This is not a requirement of that it's actually bell-shaped, just that it's symmetric. Okay, so let's do this. So the procedure to find your test statistic. For each pair of data, find the difference, D, by subtracting the second value from the first. Keep the sign, but discard any pair that gives you the difference of 0. Then ignore the sign of the differences. Sort the differences from lowest to highest. Replace these differences by the corresponding rank. And get rid of, the zeros. When you have a tie, then assign them the mean of the tied ranks. Then attach the sign. And so, insert those signs that were ignored in step 2. So in step 2, we ignored the signs. Put them back. And so put back the signs. So, we had like a ranking of 3, 4, 5. Sometimes then maybe the ranking now becomes -3 because the sign was negative. Find the sum of the absolute values of the negative ranks. Find the sum of the positive ranks. And so let n be the number of pairs of data for which the difference is not 0. The number of negative ranks plus the number of positive ranks. Let's determine the test statistic as follows. And so let eta be the population median. Let n be the sample size minus, again, get rid of all the zeros. If n is large, then the then t is approximately normally distributed with mean n times n plus 1 over 4 and standard deviation radical n times n plus 1 times 2n plus 1 over 24. Compute the sum of the ranks for the positives, for the negatives, and compute the minimum. So let's actually calculate the test statistic for t plus, t minus, and then the actual test statistic t. For the null hypothesis, eta equals 20 for the following observations: 15, 20, 15, 22, 20, 12, 17, and 26. So here they are, 15, 22, 20, 12, 17, 26. So let me do the rank. So let's subtract 20 from each of these. And so -5, 2, 0, get rid of that. -8, -3, 6. Okay, so let's see, what's the smallest guy here? 2. So the smallest is a 2. Ignore the pluses and minuses. So let's ignore the pluses and minuses, and let's sort these from smallest to largest. So if I sort this from smallest to largest, it is a 2. I guess I'll just put it here. So this is the sorted. Two, 3, and this is ignoring the signs. 2, 3, 5, 6, 8. Okay, good. So 2, oh, here it is. I guess I ignored the sign. So 2, 3, 5, 6, 8. So the rank, the unsigned rank, is 1, 2, 3, 4, 5. There are no ties. Okay, good. There are no ties. So the 2 has a rank of 1. Okay, good. The 3, which is -3, has a rank of 2. So it's a -2. So this will be, well, maybe I should put the signed rank. So I'll put the minuses. The 5 is negative. So it has a rank of -3. The 6 is positive, so it's a rank of 4. The 8 is negative, so it has a rank of -5. Okay, so now, or you could, and this is the way I usually do it, or what I do is I just put in, this is easier, I just put in all the ranks and then notice if they're positive or negative. So I just put the, so this is negative, positive, negative, negative, positive. So now let's compute t plus. So let's look at all the pluses. So 2 plus 6 is 8. I'm sorry, I added the wrong thing, you stupid jerk. I look at all the positives. So I'm sorry, this is the ranks. I look at all the positive. 1 plus 4 is 5. I look at all the negatives. 3, 5. So that's 5 and 5 is 10. And so t minus is 10. 5 is smaller than 10, so t is 5. Okay. So now let's do the same thing. Okay, so compute t plus, t minus, t. For the null hypothesis, eta is equal to 6 for the following observations. So 10, 14, 8, 6, 7, 4, 12. Okay. Bigger than 6, bigger than 6, bigger than 6. Same as 6, get rid of everything. Bigger than 6, less than 6, negative. Bigger than 6. Okay. So now, subtract 6. So 4, 8, 2, 1, negative 2, 6. Okay, so now let's rank these. So 1, 2, 3, 4, 5, 6. So there it is. Those are the ranks. But there's a tie here. These are both 2s. So there's a tie. And so the average of 2 and 3 is 2.5. Okay, so now let's add up all the pluses. And so 10, 12.5, 13.5, 18.5. Let's do all the minuses. There's only one of them, 2.5. So T is 2.5. Any questions about these test statistics? Okay, good. Okay, so now, so we had to sort of do the technical stuff first to see if you could figure out how to calculate the test statistic. Okay, so now a travel agency that promotes a particular holding resort advertises that the median cost per day of a motel in a city is $50. That's not bad. A cautious traveler selects a random sample of 8 motels in that city and records the cost in dollars per day as follows: 52 to 47. Use the Wilkinson sign rank test at the 10% level of significance to test the travel agency's claim. And so the claim is the median is 50. So the null hypothesis, eta is 50. Alternative hypothesis, eta is not 50, and alpha equals 0.1. Okay, so let's do this. I have here 1, 2, 3, 4, 5, 6, 7, 8. But I want to get rid of that 50. So 1, 2, 3, 4, 5, 6, 7. There's 7, so n is 7. Alpha is 0.01, two-tailed. The critical value is 4. And $28. So it is 4 and from 24 to 28. But maybe I should. Oops. Okay, so okay. So that's my rejection region. Two-tailed. Okay, so let's figure out my test statistic. And so I have here 52, 51, 49, 50, 53, 52, 48, 47. So let's see, 52 is bigger. So let's look at all the ones that are larger. I'll put a plus sign, plus, plus, less, negative, greater, plus, plus, less, negative, negative. Okay. Let's look at the difference. Oh, almost everything's a tie. And so 2, 1, -1. They're the same, get rid of this. 3, 2, -2, -3. Okay, so the ones are a tie. So 1, 2, and then the 2s are a tie. So 1, 2, then 3, 4, 5. The 3s are a tie. 6 and 7. Okay, so lots of ties here. So there are a whole bunch of ties. Maybe I should. So 1 and 2 are a tie. And the 2s are a tie. And the 3s are a tie. Okay, so those are all ties. Okay, so the average of 1 and 2 is 1.5. So I'll give a rank of 1.5. The 3, 4, and 5, the average is 4. So I'll give a rank of 4. The average of 6 and 7 is 6.5. So I'll give each of these a 6.5. So everything is tied. Okay, so let's find T plus. So 4 plus 1.5 plus 6.5. That's 7, 8, 12, 16. So T plus is 16. Let's look at T minus. 1.5, 7, 8, plus 4 is 12. And so T is 12. My test statistic is not in the rejection region. So I do not reject the null hypothesis. So yes, there's insufficient evidence to reject the claim that the median is 50. Again, use the classical method for the Wilkinson sign rank test, the test hypothesis. The median number of days automobiles remain in the long-term parking lot. BW1 is 3 days. The results of random sample of 32 automobiles indicate the following days: 4, 5. Alpha is 0.02. So I'm testing that the median is 3. So eta, so the null hypothesis, eta is equal to 3. And the alternative hypothesis, eta is not equal to 3. And alpha is equal to 0.02. So let's calculate my test statistic. Okay, so there are a lot of numbers here. So I'm going to do this as a frequency distribution. So there are 4 2s. So there are 4 2s here. 1, 2, 3, 4 2s. There are 7 3s. 2, 3, 4, 5, 6, 7 3s. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 4s. There are 1, 2, 3, 4, 5, 6 5s. There's 1 6. 1, 2, 3 7s. 1/8 and 1/9. Okay, so it's 4. Get rid of the 3. So get rid of these guys. Plus 9, 13, plus 6, 19, plus 1, 20, plus 3, 23, plus 1, 24, plus 1, 25. Okay. So let's find the rank here. And so I have here, I start at, this is my cumulative. So I start at 1 and I end at 4. So the numbers between 1 and 4 are all equal to 2. So 1 plus 4 divided by 2 is 2.5. Times 4 is 10. Okay, next. I have here 13 of these. Okay, so I go from the next number, which is 5 to 13. So 5 plus 13 divided by 2 is 9. Times 9 is 81. 19. 14 plus 19 divided by 2 is 16.5. Times 6 is 99. 20, it doesn't matter. 20 times 1 is 20. 23. 21 plus 23 divided by 2 is 22. Times 3 is 66. 24 times 1 is 24. 25 times 1 is 25. Okay, good. So let's figure out T plus. So let's do the pluses. Actually, let's see. We want this to be less than 3. Oh, so these are minuses. The rest of these are pluses. Okay, so everything else are pluses. Okay, so T plus is 81 plus 99 plus 20 plus 66 plus 24 plus 25, 315. T minus is, well, there's only one T minus, 10. So the smaller number is 10. The critical value was 77 for n equal 25 and alpha is 0.02. So my test statistic is in the rejection region. So I reject the null hypothesis. So I reject this null hypothesis. And so, no. There's insufficient evidence to support the claim that the median is 3 days. Let's do the following example. The following table of ages of best actresses and best actors. The data are matched by year in which the awards were won. Use the sample data to test the claim that there's no difference between the ages of best actresses and best actors. Use the Wilkinson sign rank test with a 0.05 significance level. So I believe we already did this before, but using a different test. So the data are simple random sample. And well, if I looked at a histogram of the differences of the this third row here, the left side should be roughly a mirror image of the right side, which does not appear to be the case, but with only 10 differences, the difference between left and right sides is not too extreme. So we'll consider this requirement satisfied. And so, you know, it's not quite symmetric, but it's not so bad. I mean, if it looked, there's a little bit more over here, then it would look symmetric. So it's not too bad. We just had to interchange these two, then it would look quite symmetric. So it's not too bad. It's been a little bit shifted over, that's all. So let's take the difference. 28 minus 62, negative 34. 63 minus 52, 11. 29 minus 41, negative 12. 41 minus 39, 2. 30 minus 49, negative 19. 41 minus 41, 0. So get rid of this guy. 28 minus 44, negative 16. 26 minus 51, negative 25. 29 minus 54, negative 25. 29 minus 50, negative 21. Okay. So the null hypothesis is that there is no difference. A sub d is equal to 0. The alternative hypothesis, there is a difference. A sub d is not equal to 0, and alpha equals 0.05. Okay, so let's do this. Oh, we're going to do it in steps. Okay, so we calculate this. So let's look at the rank here. And so first, second, third, fourth, fifth, sixth, 7, 8. Tied 9. So the 7 and 8 were tied. So I'll give them a ranking of 7.5 each. Okay, so these are negatives. Add up all the pluses, 3. Add up all the negatives, 12, 17, 27, 30, 37, 42. So 42. And so they're 3 and 42. And so the test statistic is 3. The critical value was 6. I'm in the rejection region. My test statistic is in the rejection region. So I reject the null hypothesis. So no, there's insufficient evidence to support the claim of no difference between the ages of the best actress and best actors. So let's do a median claim about a median of a single population. Data set 3, body temperatures in appendix B, includes measures body temperatures of adults. Use the 106 temperatures listed for 12 a.m. on day 2 with Wilkinson sign rate test to test the claim that the median is less than 98.6. Use a 0.05 significance level. So we would say that this is a simple random sample, and it's approximately symmetric if you look at the histogram. And so we're going to pair the sample value with the median. And so T would equal 661, which gives us a Z value of negative 5.6, a critical value of negative 1.645, two-tailed. Two-tailed 0.05. Let's see. Two-tailed 0.05. Yeah, okay, so two-tailed 0.05. That's correct. And I have a test statistic that is in the rejection region. Okay. Yeah. And so since the test statistic is in the rejection region, we reject the null hypothesis. So I rejected the null hypothesis. And so, yes, there's insufficient evidence to reject the claim that the median body temperature is less than 98.6. Any questions on section 3.3? Okay. Let's go on to section 3.4. Yeah, so maybe we'll do it. So let me go on to section 3.4. The Wilkinson rank sum test for two independent samples. Caution, do not confuse the Wilkinson rank sum test for two independent samples with the Wilkinson sign rank test for matched pairs. And so the Wilkinson rank sum test for is a non-parametric test that uses the ranks of sample data from two independent populations. The null hypothesis, two independent samples come from a population with equal median. The alternative hypothesis is, well, either that the two populations have different medians, or one median is less than the other or greater than the other. And so my null hypothesis is that it's equal to medians. Alternative is that's either not equal to, greater than, or less than. So let N1 be the size of sample 1, N2 the size of sample 2, R1 the rank of sums for sample 1, R2 the rank of sums for sample 2, B doesn't really matter. We pick the sum of ranks for sample 1. Mu sub R be the mean of the sample R values that is expected when the two populations have equal medians. Sigma sub R, the standard deviation of the sample R values that is expected when the two populations have equal medians. So requirements are that I have two independent samples, simple random samples, and the two samples have values of greater than 10, so I can use a normal approximation. If the two populations actually are normal, then you don't need this requirement of 10. So the test is this: Z equals R minus mu sub R over sigma sub R, where mu sub R is equal to N1 times the quantity N1 plus N2 plus 1 over 2. Sigma sub R is the square root of N1 times N2 times the quantity N1 plus N2 plus 1 over 12. N1 is the size of the sample from which the rank sum R is found. N2 is the size of the other sample. R is the sum of the ranks from some of the ranks of this sample. And so we basically calculate it the same way we did from before. So let's do the following example. Course evaluation ratings for female and male professors. The table listed lists course evaluation rankings for courses taught by female and male professors. Use a 0.5 significance level to claim that male and female professors have the same median course evaluation ratings. And so sample data are from two independent simple random samples. Sample sizes 12 and 15 are both greater than 10, so the requirements are satisfied. So, null hypothesis. The median of the course evaluation rating for courses taught by female professors are equal to the median course evaluation rankings for courses taught with male professors. Alternative hypothesis is that the median for females is not the same as the median for males. The rank, the combined list of all 27 course ratings begin with rank 1. And so, and again, if there's ties, you have to deal with the ties. So here they all are. Okay, so female professors, male professors. Okay, so we go from smallest to largest. Okay, so 2.9 is 1. Next, let's figure out the second. 3.1. Then 3.3. Then 3.4. So these are ties. So I had 1, 2, 3. Okay, so 3.4. Okay, so those are all ties here. Okay, so I have here, so this is 3. So this would be 4, 5, 6, 7, 8. Okay. Okay, so let's add these up. And so I get here 4 plus 5. Maybe let's do it on the other side. 4, 5, 6 plus 7 plus 8 to 4 divided by 5. Okay, so that's going to give you 10, 20, 10, and 20 is 30 divided by 5 is 6. So I should get, so 30 divided by 5 is 6. So I should give each of these a ranking of 6, which I did. Okay, next. So 3.4. Okay, so now seven. 3.4. Of a 3.7. Okay, 3.7 is the 9th one. Okay, then let's do 3.8. Oh, I have a 3.8 here. I have a 3.8 here. Okay, so this is 9, 10, and 11. Well, obviously the average of 10 and 11 is 10.5. I'll give them all a 10.5. Okay, now 3.8. So let's do 12. So 3.9 is 12. Okay, then a lot of numbers here. 13. Okay, so 3.9. So I'm at 3.9. Okay, so I don't see 4.0. Okay, so I have this, so that's 12. So I'm at 13. 14. 15. 16. Okay, so those are all tied. I should probably put blues here for the 4. 13, 14, 15, and 16. Okay, so let's do that. So I get 13, 14, 15, 16 divided by 4. Okay, so that's 10, 20, 30, 40, 40, 50, 8. So 10, yeah, 58. 10, 20, 30, 40, 58, which is 58 divided by 4. 29, 14.5. So I should replace each of these by 14.5. Okay, which I did. Okay, so now we're at 17. Okay, so 4.0. We're at 4.0. Okay, what's greater than 4.0? 4.1, 17. Okay, 4.1 is 17. Okay, now go for 4.2. Oh, 4.2 is 4.2 is here. That's, we already had 17. That's 18 and 19. So average of 18 and 19 is 18.5. And then let's go for 4.3, which is 20. Oh, here's 4.3. 20, 21, 22, okay, so we're 22. Okay, so it would be 20, 21, and 22. 20, 21, 22 divided by 3. So that's 63. Huh? 20, 21, and 22. That's 63, which is average is 21. Okay. 21, 20, 21, 22. Let's just see if there's another 20, 4.3. Let's see if there's another 4.3 I'm missing. Yes, there's another 4.3 I'm missing right here. 23. Sorry, there's a plus of 23. I'm missing one of them. So plus of 23. Okay, over 4. Okay, so that's 20, 40, 60, 80, 6. Divided by 4, 23. Divided by, so it's a 23 divided by 2 is 23. 43 divided by 2. 43 divided by 2, sorry. 43, which is 21.5. Okay, so I replace each of these. Maybe I should have a green or something. So I replace each of the 4.3s by 21.5. Okay, so now I'm at 4.3. 4.4. Okay, so I have a 4.4, which is, I'm at 24 now. 4.4. I'm at 25. So average of 23 and 24 is 24 and 25, sorry, is 24.5. Okay, and then so I'm at 4.4. So 4.5 is 26. 4.6. 4.7 is 27. 4.8. I don't think I have it. So I think I have everything. So these are done. These are done. Yeah, I'm done. So that was the highest score. Okay, so there are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers. There's a total of 1, 2, 3, 4, 5, 6, 7, 8, 15 numbers. Okay, good. So there. Oh, and if I add up all these numbers, so add up all these numbers here in red, I get 167. Add up all these in red, I get 211. Okay, so here it is. So let's calculate Musa bar. And so Musa bar is equal to 12 times 12 plus 15 plus 1 divided by 268. Sigma bar is equal to the square root of 12 times 15. Yeah, put it this way. The square root of 12 times 15 times the quantity 12 plus 15 plus 1 divided by 12. And so that gives you 20.4939 extra digits. And so I have here, I'll use the 167. So I'll use the 167. I'll use the females. So let's use the females. And so I have here Z equals X, which in this case is 167 minus mu, the 168 over sigma, the 20.4939, to give me a negative 0.0484795036, which is
Sorry
not.
to interrupt, Professor.
Yes, question.
So I gotta go. So I'm just gonna finish the meeting. Like I'm gonna watch the recording later.
Yes, that is fine.
Is that okay? Thank you.
Okay, bye-bye. Okay, so my test statistic is not in the rejection region. And so I do not reject the null hypothesis. So there's insufficient statistical evidence to warrant the rejection of the claim that female professors, male professors have the same median course evaluation rating. So based on the available sample data, it appears that female professors, male professors who teach courses that are rated at about the same. Okay, let's do the next example. This table here lists pulse rates for a sample of males and females. Use a 0.05 significance level to test the claim that males and females have the same median pulse rate. Okay, so again, we looked at, we group these all as one, and we rank. So first, second, etc. And then we, if there's a tie, we average the ranks. And so N1 is 12, N2 is 11, R1 is 123.5, R2 is 152.5. So these are two independent random samples. Sample sizes are both greater than 10. So the null hypothesis, the median for males is the same as the median for females. Alternative hypothesis is that the medians are not the same. And so let's determine, so I figured out each of these ranks here. And I guess I'm going to go with males this time. First column. And so my parameters are mu sub r is equal to N1, 12 times, 12 plus 11 plus 1 divided by 2, 144. Sigma sub r is equal to the square root of N1, 12 times N2, 11 times the quantity N1 plus N2 plus 1, 12 plus 11 plus 1 divided by N sub divided by 12. And so I get 16.248076873. So Z equals R, and I picked the 123.5 minus mu 144 over sigma, the 16.24, etc. I get a negative 1.26, 168,77825. My test statistic is not in the rejection region, so I do not reject the null hypothesis. And so, yes, there's insufficient statistical evidence to warrant the rejection of the claim that male samples. So, the Kruskal-Wallis test, the H test, is a non-parametric test that uses ranks of combined simple random samples from 3 or more independent populations. It tests the null hypothesis that the populations have the same median. So this is similar to, ANOVA, where we are testing the equality of 3 means, 3 or more means. But there we have to assume that they come from normal populations. Here we don't. We don't require that they come from normal populations. When we compute the test statistic H, if we can use an asymptotic estimate, if each sample has at least 5 observations, then it will be approximated by chi-square distribution. And so H statistic basically measures the variance of the ranked sums, R1 through RK. So null hypothesis is that the samples come from a population with the same median. Alternative hypothesis is that the samples come from populations where not all the medians are the same. And so capital N is the total number of observations in all the samples combined. K is the number of different samples. R1 is, let's say, the rank, the sum of the ranks for the sample 1. N1 is the number of observation for sample 1. R2 is the sum of ranks for sample 2. N2 is the number of observations of sample 2, etc. Our requirements are that we have at least 3 independent simple random samples. And each sample has at least 5 observations for us to be able to use the following. That H, sorry, H is equal to 12 over N, sorry. Okay. H is equal to 12 over N times N plus 1 times R squared over N1 plus R squared over N2 plus R squared over N3 plus dot, dot, dot. R sub K squared over N sub K minus 3 times N plus 1. And so we'll be using a right tail test, and we'll be looking at your chi-squared critical values, where nu is equal to K minus 1, the number of samples. So again, you temporarily combine all the samples into one big sample, and you rank each of them, and you then find the sum of the ranks and the sum of the sample sizes, and you calculate H from this. So let's do each of these. The effect of lead on IQ scores. So the table below lists performance nonverbal IQ scores from samples of subjects with low blood lead level, medium blood lead level, and high blood lead level. So 80 to 97. Use a 0.05 significance level to test a claim that the 3 samples have a performance IQ scores that come from populations with medians that are all equal. Okay, so the requirements are that each of the 3 samples come from independent random samples. Yes. Each sample size is at least 5. Good, so we can use the an asymptotic estimate. So I can use this asymptotic chi-squared approximation. And so null hypothesis is that the median for low lead blood level, the same as for median, the same as for high blood lead level. The alternative hypothesis is they're not all the same. And alpha is 0.05.
Okay.
Okay, so let's look at this. So just like before, same thing. I'm not going to go over it too much. So I combine these all in one big. Yeah. So I combine these all. Sorry. So I combine these together. Sorry about that. There. Okay. So I combine these all. And let's see, the smallest is 64, then 78, etc. And if I have any ties, I have to find the average. Just the same as always before. And there are 8 numbers here. And you add up all these, get 86, 50.5, 53.5. Okay, so same that we've been doing previously. And so I have here H is equal to 12 over N. That's going to be 11, 19. 19 plus 1, R1 squared. So it's 86 squared over 8 plus 50.5 squared over 6 plus 53.5 squared over 5 minus 3 times N, 19 plus 1. 6.694. Okay, good. My degrees of freedom are, well, 1, 2, 3, 2. Okay. And so my critical value is degree of freedom is 2. And alpha is 0.5. And so my critical value is 5.991. Test statistic is 0.694. My test statistic is not in the rejection region, so I do not reject the null hypothesis. So no, there is insufficient evidence to reject the claim that 3 samples performance IQ scores come from population with medians that are all equal. The population medians do not appear to be significantly different. Any questions on section 13.5? So it's all, once we've done this a few times, then you sort of see the pattern. So first you had to sort of see it, what we're doing at the beginning with all these ranks and ties and all that. But once we've told you how to deal with them, everything looks very similar. So there's no real difference other than, obviously the actual calculations are different, but the ideas are the same. Okay, let's go on to section 13.6. So section 13.6, rank correlation. And so Spearman's rank correlation test. The rank correlation test, or Spearman's rank correlation test, is a non-parametric test that uses ranks of sample data consisting of matched pairs. It's used to test for the association between 2 variables. So it's very similar to Pearson's product moment correlation coefficient. There, you were testing to see if there was a linear correlation. Here, we're just seeing if there is a monotone correlation. And so the advantages of Spearman's rank correlation is that, well, the non-parametric test of rank correlation can be used in a wide variety of circumstances as compared to the parametric model for Pearson's product moment linear correlation. With rank correlation, we can analyze paired data that are ranks or can be converted to ranks. So anything that can be converted to a rank can be tested. Does not require, that it's a normal distribution or anything else. Only that if you can convert your data to a rank, if it's ordinal, as long as it's ordinal data, then we can use this. So this can be used for any ordinal data. Maybe I should actually say this. This is ordinal data. Rank correlation could be used to detect some, but not all relationships that are nonlinear. It can determine monotone relationships, meaning that it's, if it's somehow increasing. So, if there's some sort of increasing relationship, it can determine that. So the null hypothesis that rho sub SP is 0. There is no correlation between the two variables. Alternative hypothesis, rho sub SP is not equal to 0. Our requirements are that the paired data are a simple random sample, and that the data are ranks or can be at least converted to ranks. So, and the formula is identical. If you look at the value of R, it's the same formula, just it doesn't mean quite the same thing. So convert to ranks, then plug into the formula. R sub SP is n sum of xy minus sum of x sum of y over the square root of n, sum of x squared minus sum of x quantity squared times the square root of n sum of y squared minus sum of y quantity squared. So if there are no ties, so if I have no ties, it turns out that I can actually use a simpler formula. So assuming that there are no ties, then we have the following, that R sub SP is 1 minus 6, the sum of d squared over n times n squared minus 1. So that's a much easier sort of test here. For large values of n, say n greater than or equal to 30, then R sub SP times the square root of n minus 1 can be approximated as a normal, a standard normal distribution. And so R sub SP is the rank correlation coefficient for a sample pair data. So R sub SP is a statistic. Rho sub SP is the rank correlation coefficient for population data. It is a parameter. D is the difference between the ranks for the two XY values within a pair. N is the number of pairs of sample data. F, so basically just sort of change, if there was no SP here, if there was, Pearson's product moment correlation coefficient, change this to linear, this from linear to monotone, and then you get the same sort of, expressions. So if R sub SP is equal to 1, then the relationship between X and Y is perfectly monotone increasing. So what is monotone increasing? It means that it's always going up and never going down. So this is not monotonic. Increasing if it's going up, monotone decreasing if it's going down. And so if R sub SP is equal to -1, then the relationship between X and Y is perfectly monotonically decreasing. What's that extra M doing there? Okay. If R sub SP is equal to 0, then there is no monotone relationship between X and Y. It looks something is going up, sometimes down and up and down, and you can't tell when it's up and down. So disadvantages. Oh, the efficiency. A minor disadvantage of rank correlation coefficient is its efficiency rating of 91. This efficiency rating shows that with all other circumstances being equal, the non-parametric approach of rank correlation requires 100 pairs of sample data to achieve the same result as only 91 pairs of sample observation analyzed through the parametric approach, assuming the much stricter requirements for the parametric approach are met. Okay, so let's compute this. So I didn't compute this for some reason. Okay, so compute Spearman's rank correlation coefficient. Okay, so 314, 822, 10, 24, 2, 16, 6, 16, 13, 20. Okay, so let's look at D. Doesn't matter which one I call it. So let's just do 11, 14, 14, 13, 20, 10, 7. Okay, so those are the differences. Unfortunately, there's a tie. So if there was no tie here, then I would be good. I could just use, I could do this. I could use this formula. So if there was no tie, but there is a tie, then I could use this formula. Otherwise, well, I use the same formula that I had for doing the linear correlation coefficient. But instead of inputting the numbers, I input the ranks. Okay, so let's input the ranks here. And so let's find the ranks. Maybe I'll do ranks. And so this 1, 2, 3, 4, 5, 6. These are both 4s and 5. So on average, it's a 4.5. Okay, so now let's put that into my calculator. So I'll just put this into my calculator. And so I'll do 2, 4.5, 3, 1, 6. 2, 4, 6. Okay, so let's store that. Oops. In L1. Okay, and now let's do calculate there. Oh, here, wait 1 second. Oh, and then the Y's here. Oh, stupid jerk. Let's calculate. Let's change all those to ranks. I'm sorry. Rank. I said it, but I didn't do it. I'm sorry. This is 1, 2, 3, 4. 5, 6. And then this is smallest is 14. 1, 2, 3, 4, 5, 6. Okay. I didn't put them as ranks. I ranked the differences, but I didn't rank the actual data. Okay, so let me put in, sorry, I forgot to put it into the, okay, so sorry about that. Okay, so let's get rid of that guy. Okay, so 2, 4, 5, 1, 3, 6. Store that in L1. 1, 5, 6. 2, 3, 4. So that in L2. Okay, so now let's calculate linear regression. Okay, so R is equal to, so you then plug in here. So R is equal to 0.7714 2857 2857. Okay. Okay, so that's pretty good. So it's relatively monotonically increasing. So it seems to be more or less monotonically increasing. Okay, so let's continue here. Do better televisions cost more? The table below lists ranks and cost in hundreds of dollars of LCD televisions with screens of at least 60 inches based on data from consumer reports. Find the value of rank correlation coefficient and use it to determine whether there is sufficient evidence to support the claim of a correlation between quality and the price. Use a 0.05 significance level. Based on the result, does it appear that you get better quality by spending more? And so here are the quality rank and the cost. So the sample data are simple random sample from the televisions that were tested. We can convert this into ranks. And well, certainly this is not normally distributed. Okay, so let's test this. So null hypothesis, rho sub SP is 0. Alternative hypothesis, rho sub SP is not equal to 0. And let alpha equal 0.05. Okay, so let's convert these to ranks. Maybe I'll put the ranks below it and then I'll show you the ties. So 1, 2, 3, 4, 5 ties. 6. What the heck happened to 16? I don't know. Stop. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the average of these is 5.5. Okay, good. So 5.5, 10, 5.5, 3, 8, 7, 1, 2, 9, 4. Okay, good. And well, obviously these rankings is the same because smallest is done smallest to largest. So it's already been converted to ranks. Okay, so there are ties. Let's see. Oh, there was a tie. So there were ties. Okay, so oh, actually, I forgot. Was there a tie here? Here, wait. There wasn't a tie there. So I could actually also use, let's see if this works. Let's also use this formula. 1 minus 6 sum of d squared over n squared minus 1. Okay. So I have here, square all these numbers, add them up. So actually I can go back here. Oh, I didn't do the differences. So I didn't do the differences. And so let me just check here. Well, I guess I'll have to do those. And I only need it squared. Okay. $831. That's 5, 2, 4, 6. Okay. No. Okay, so no, you should be able to. Yeah, whatever. Okay, so I get something different. We'll forget that. Okay, so let's do that. Let's continue. Where is that? Okay, so let's start over again. Oh, so I was here. So let's figure out the the Spearman's rank correlation coefficient. And so I get here n 10, sum of x, y, 280 minus sum of x, 55, sum of y, also 55, over the square root of n, 10, sum of x squared, 385 minus sum of x, 55 squared, times the square root of n, 10, sum of y squared, 384.5 minus the sum of y, 55 squared. So I get a negative 2.2735574,947. My test statistic is not in my is not in the rejection region. So I do not reject the null hypothesis. And so there's insufficient evidence to support the claim of a correlation between quality and cost. So based on the sample data, it appears that you don't necessarily get a better quality by paying more. Use the measured systolic and diastolic blood pressure of 147 randomly selected females from data set 1 in Appendix B. Use a 0.05 significance level to test the claim that among women, there's a correlation between systolic and diastolic pressure. Okay, so I'm going to do the following hypothesis test. This is a simple random sample. These can be converted to ranks. If you actually calculate Spearman's correlation coefficient, you get 0.354. There are 147 pairs of data. N is 100, and so N is 147, which is greater than 30. Let's find the critical values. And so if you do that, you get point plus or minus point. We're going to do it this way. Okay, so you can do it either way. So I'll do this way. Plus or minus 0.196 divided by the square root of, so this is for the critical values. Maybe I should just say that looks bad, so the critical values. Plus or minus 1.960 divided by the square root of 147 minus 1, plus or minus 1.62. The test statistic lies in the rejection region. Therefore, I reject the null hypothesis. And so I rejected the null hypothesis. And so it was not equal to 0. So there is sufficient evidence to support the claim that among women, there's a correlation between systolic blood pressure and diastolic blood pressure.